our lecture for today. Okay.
Okay, doktor, boleh.
Alright. Okay. So last week, I think the other week, Sugi, you cannot make it, and then last week I didn't do the class because I wasn't feeling well. So I think Sugi, you missed almost one chapter lah. Chapter 2 tu, I think you completely missed the chapter of chapter 2. So nanti Sugi, make sure you tengok the video, the video for the chapter 2 lecture and the tutorial as well. So I already finished basically chapter 2 entirely lah, lecture dan juga and also the tutorial. If you have any questions, nanti Sugi, you go through. If you have any questions, please contact me anytime that you can. I will try to help you lah, to assist you in the problem. Okay tak, Sugi?
Okay, doktor, boleh.
Alright, okay. So today, we're already going to chapter 3 for the course, right? So chapter 3 is another chapter which is a bit tough. Chapter 2 is actually considerably not that difficult. So that's why if you see the video should be enough. But chapter 3 is slightly more complicated because now chapter 3, it goes a little bit towards mass balance already. So you have done mass balance in another course, which is what we call as CPP. In CPP, we did energy balance and also mass balance. So this chapter touches a little bit on mass balance, or I would say it offers another way of doing mass balance for reactive process. But before we go there, okay, so we will first learn a few important things that will help us in designing reactors. Okay, so if you remember in chapter 2, we have derived the design equation, meaning if I have reaction time, I want to find the reaction time for a batch reactor, I have a design equation. For the flow reactors, we have CSTR, we have PFR. So CSTR is a continuous stir tank reactor, PFR is the plug flow reactors. So if you realize in chapter 2, we did try to find the volume of the reactors, okay? But in chapter 2, we do that when we are given two important information, which is conversion and minus RA, which is the rate of reaction. So as I told you before, how do we quantify a reaction? It's through rate of reaction. So rate reaction 2 actually is we monitor the number of the concentration of the compound with time. Okay, so rate of reaction means we can actually evaluate in terms of rate of disappearance, rate of formation. Then rate of disappearance, rate of formation of which compound. So for example, if we are measuring the rate of disappearance of compound A, so it's called minus RE. Okay, so as you know, since we have many compounds and we can measure many concentration, therefore the rate of reaction tu ada banyak kan? We can do for A, for B, for C, for D. So it'll be very confusing if everybody is measuring different types of compound. So what do? We only measure one compound, so we call it as compound A. So how do you define a compound A? So compound A too is the reactant. It must be a reactant. So if you have one reactant, automatically that reactant will be your A. However, if you have two reactant or more than one reactant, we will always consider the limiting reactant as your A. Means we will only measure concentration of A with time, then we will get the rate of reaction, which is minus RE. So in chapter 2, the information is provided to you, meaning your assumption, someone has already done the lab work, someone has already measured at each conversion, how much is the minus RE, so then I find the volume of the reactor. Okay, so that's why chapter 2 is easier in that sense, because the value of minus RE is given to you. However, it's not always necessarily the case. Okay, not necessarily you will always obtain or you will always get the minus RE data for you to design the reactor. So in chapter 3, we are going to study how do we actually obtain this minus RE. So rate of reaction, rate of reaction ni kita measure in terms of minus RA. Minus R, rate of disappearance. A is for compound A, so minus RA, rate of disappearance of compound A. So how do we determine minus RE? So minus RE is determined based on a power law model. We call this as power law model, where they have certain terms in the power law model in order for us to find minus RE. So these terms are, first we will see there's a K. So K is what we call as reaction rate constant. Okay, so minus RA reaction rate. K is reaction rate constant, pemalar kadar tindak balas. Okay. In bracket, you will see we have Ca, Cb. So if you remember, C is for concentration, A is for compound A lah. So Cb, concentration of B. So you will have the concentration of your reactants. Okay, so it depends juga lah your reactants. What is your reactant? So let's say if you have one reactant, of course Ca sajalah. If you have two reactant, it can be Ca, Cb, or it can be Ca, or it can only be Cb. I will explain you later how do we determine what concentration to be inside the bracket for the minus Ra. Then if you see there's a power alpha and power beta. So why do you have this alpha and beta? This is what we call as reaction order. Okay, so reaction order, all right? So normally, okay, in a reaction or in a common reaction, this reaction order are usually zero order, first order, second order, the common ones. However, not necessarily only means it's only 0, 1, 2. It can also be third order, fourth order, so on and so forth. Okay, so alpha beta again is the reaction order. So what is the reaction order? The order of reaction is defined as the power to which a reactant concentration term in the rate equation is raised. So meaning is to say that reaction order is to the power of how much your reactant will be raised. Means katakan if second order Ca power 2 means the rate of reaction is against concentration of A power of 2, or let's say first order power of 1, or let's say third order power of 3. Okay, so that's the definition of alpha and beta. Okay, now next. Okay, so how do we call it, or how do we term this reaction order? Okay, let's say you have this reaction based on the equation above. Okay, we can say that the reaction is alpha order with respect to reactant A and beta order with respect to reactant B. Okay, so reaction order ni very specific to the reactant. Meaning, let's say if you say the reaction is first order, you must say specifically, is it first order with respect to A or first order with respect to B? Okay, so let's say the reaction is first order with respect to A and first order with respect to B. You can't just say the reaction is second order. Sebab kalau you say the reaction is second order, there's actually three possibility. Meaning, it can be first order with respect to A, first order with respect to B, overall order is 2. You can also say second order with respect to A is also 2. Or you can also say second order with respect to B is also 2. So when you want to say second order, you have to specify very clearly this second order is towards what reactant. Okay, so for example dalam case ni, okay, let's say we say first order with respect to A and first order with respect to B, hence overall order 1 plus 1 is second. So overall order second has different implication. Overall first order pun ada different implication. As I said, kalau overall first order, it can be either first order with respect to A or it can be first order with respect to B. Okay, so that's why even when you look for literature, when we're talking about rate law, they will always mention specifically the reaction is what order with respect to which reactant. Okay, so to prevent the confusion about this matter. Right, so next one. Okay, but before I go further, perhaps you would like to understand what is this reaction order? What is the implication of having reaction order? Okay, so in a simplest way, let me give an example. Let's say your reaction is 1A and 1B reacting with 1C and 1D. Okay, so let's say you find from literature, they says the reaction is first order with respect to A and first order with respect to B. So what does it mean? It means in the reaction, okay, in the real mechanism of the reaction, it is between 1A, it can be atom, it can be molecule, it can be ion, but the concept is 1A will react with 1B. Okay, so means you imagine one molecule A, one molecule B, they react, they combine, they will get product. Okay, so that's what it means if they say the reaction is first order with respect to A, first order with respect to B. Okay. So if the reaction really occurs the same as the chemical equation. Kalau you perasan dalam chemical equation ni, let's say dia kata 1A react with 1B. So really the mechanism of the reaction, really one molecule A react with one molecule B. So if they read the mechanism or the rate really follows the chemical equation, we call it as elementary rate law. Meaning rate law dia tu really follows the chemical equation. Okay, so katakan if the equation say 1A react with 1B, hence the reaction is first order with respect to A and first order with respect to B. Means reaction order dia follows the stoichiometric coefficient in the equation. If the reaction really follows stoichiometric coefficient, we call it as elementary rate law. So rate law dia terus first order with respect to A, first order with respect to B. However, it's not always necessarily that way. Means dalam reaction tu tak semestinya dia akan, rate law tu akan ikut chemical equation. So what do I mean by that? Okay, you must understand. Reaction doesn't occur only in one pathway. Maksudnya contohnya, if the reaction, katakan reaction dia punya chemical equation says 1A reacting with 1B. Okay. When you really examine the reaction, dia tak semestinya hanya satu tindak balas atau satu pathway of 1A and 1B. Most of the time, reaction will undergo a few pathway, or we call it as mechanism. Okay, katakan untuk tindak balas untuk berlaku, dia akan ada banyak pathway baru tindak balas itu boleh berlaku. So, when we want to evaluate the rate law, bila you have a lot of pathway dalam satu tindak balas, definitely you will get confused, right? Rate law ni berdasarkan pathway mana when you have a lot of pathway. So a lot in this many pathway, there will be one pathway yang kita panggil sebagai rate determining step. Ataupun pathway inilah yang kita gunakan untuk kira dia punya minus RE. Okay, so there are cases of which, katakan, the reaction chemical equation says the reaction is 1A plus 1B to produce C and D. However, the pathway for that reaction to occur, maybe the first pathway is first, A has to decompose first. Means A kena pecah dulu, then baru tindak balas boleh berlaku dengan B. Or it's also possible, two molecules of A have to combine first, baru can react with B. Or it's also possible maybe molecule B yang have to be combined first. Two B have to combine, baru dia boleh react dengan A. Ataupun B has to decompose, then only boleh react dengan A. So what are these implications? Okay, let's see, katakan the steps in this reaction, one of the step ataupun the rate determining step is first, ataupun rate yang determining step tu adalah A tu has to combine first. Means 1A has to combine with 1A first, then only can react with B. If that's the rate determining step, hence the reaction order will become minus RA equals to KCA power of 2. Second order with respect to A. Means 2A combine, baru boleh react dengan B. Okay, that's why it's second order. Okay. So let's say if it's first order, meaning let's say katakan order reaction dia adalah minus RA equals to KCA. Okay, so means 1A tu have to decompose first, maybe split ke ataupun dia decompose, then only boleh react dengan B. Itu pun possible. So the rate law become minus RA equals to KCA. So what I'm trying to imply is reaction order tu is to indicate how actually the reaction really occurs. So kalau first order is usually the molecule has to decompose first. Dia kena pecah dulu, tindak balas. Second order is normally the combination of the molecule. Means dua molecule tu bergabung, power of 2 lah. So that's why I said it's very rarely is third order ataupun fourth order. Sebab kalau third order involve 3 molecules or 3 atoms, which is quite rarely can occur in a reaction. So as you know, the common reaction is definitely decomposition, combination. Okay, so that's the most common one. So that's why if you have 2 reactant, the most common one will be KCA, the common one will be first order with respect to A, first order with respect to B. Means 1A combine dengan 1B, which is the most common one. But as I told you, ada juga reaction yang mana molecule tu kena either A tu have to decompose or have to combine, then only can react with B. That's why sometimes reaction order tak follow the stoichiometric coefficient, which we will discuss later. Okay, so come back to this. Alright, so let's say if the reaction follows elementary rate law. So how do we know this? Jadi kita nak tahu reaction tu follows atau tidak elementary rate law. It has to be done experimentally. Okay, you cannot just tengok reaction tu kita agak dia elementary ke tak elementary. You cannot. You have to actually do the experiment. You gather the data, you analyze, and then you will then determine does this reaction follows elementary rate law or non-elementary rate law. So even if you are trying to look for rate law, this rate law for reaction, you must understand most of the common reaction, rate law dia orang dah cari because people will do this experimentally. Okay, right? So if you look from literature, they will provide you this information. The reaction follows elementary rate law, or they will say the reaction is non-elementary rate law. So means dia dah tak ikut rate law, tak ikut elementary rate law lah. Okay. So again, how do we know? As I told you from literature, but if it's elementary rate law, then for you to deduce the reaction order is straightforward. Okay, the reaction order of the compound in the reactant follows the stoichiometric coefficient. Meaning, contohnya dalam reaction ni is 1A react with 1B. Hence, the reaction will be first order with respect to A, first order with respect to B. So the rate law become minus RA equals to K. K is always there. Regardless elementary ke non-elementary rate law, the K is still there. Okay. The CA, CB. Because technically CA power of 1. Tapi CA power of 1 is still CA. Contohnya 4 power of 1 is still 4. 5 power of 1 is still 5. So that's why we write it as CA, CB. Technically power of 1, but again sama concept. Normally first order, you don't have to write the power. It's understandable that it is first order. Okay. So for example, case kedua, let's say you have the real reaction, it is 2NO reacting with O2 to produce 2NO2. Okay, so again, the rate law, kalau it's mentioned, this reaction follows elementary rate law, hence the rate law become minus RNO, nitrous oxide. Okay, so kita assume again kalau kamu confused, kita nak tahu A, B, C dan D. Okay, always remember dalam chemical equation, the first compound is usually your A. So kita akan kira berdasarkan your A, right? So in this example, nitrous oxide is your A. So minus RNO lah. Okay, so it means the rate of disappearance or the rate of reaction based on NO. Okay, so minus RNO, nitrous oxide equals to K. Alright, then you look for the two reactant. So the two reactant is NO and O2. So the power or the reaction order follows the stoichiometric coefficient, means it is second order with respect to nitrous oxide and first order with respect to oxygen gas. So it become K. CNO power of 2. CNO is the concentration of NO, power of 2. Concentration of oxygen gas, power of 1. Because stoichiometric coefficient for oxygen gas is 1. Okay, so that is how we deduce the rate law if the reaction follows elementary rate law. Means reaction order dia follows the stoichiometric coefficient. Okay, however, like I told you just now, it's not necessarily that case always. Tak semestinya untuk all types of reaction, the reaction order will follow the stoichiometry coefficient. So what happened in that case? So let's say katakan kalau dalam test, dalam exam, dalam literature, okay, if they mention it is non-elementary rate law, or it says it does not follows elementary rate law, hence kita dah tak boleh tengok dah persamaan kimia. We can no longer deduce from the chemical equation for the reaction order. So instead, for that case, what we do is the information has to be given to you. So katakan dalam test, dalam exam, I will provide you with the information, and if in the literature, they will tell you specifically that, okay, this is not elementary rate law, they will give you the information about the reaction order. Okay, so what do I mean with that? Okay, so again, okay, katakan we see these two examples. On your left, on your right, it's the same reaction. 1A reacted with 2B to produce 2C. However, on your left, dia kata obeys elementary rate law. On your right, tak obeys elementary rate law. Dia dah tak ikut elementary rate law. So, macam mana kita nak deduce? Okay, so kalau left side, kalau dia kata obeys elementary rate law, okay, so rate law dia akan menjadi minus RA, okay, equals to K. Then you have the two concentration, right? Your two reactant, right? So concentration of A, concentration of B. CA, CB. Reaction order dia, first order with respect to A, second order with respect to B. So become K, CA, CB power of 2. So first order with respect to A, second order with respect to B. Kita tengok saja the chemical equation. However, on your right, this is no longer elementary rate law, means this is non-elementary rate law. So the information is given to you. So let's say information dia kata the reaction is second order with respect to A and zero order with respect to B. Okay, so dia kata how to state the rate law. What's the rate law? So rate law dia become minus RA equals to K CA power of 2. So why power of 2? Because dia kata reaction is second order with respect to A. So that's why minus RA CA power of 2. So what happened to CB? They says zero order with respect to B. Okay, so kamu, if you understand mathematics, CB power of 0 is 1. Maksudnya katakan 4 power of 0 is 1. 6 power of 0 is 1. So CB power of 0 is 1. So that's why they no longer has CB in the rate law. So you can see kalau dia in elementary rate law, dia punya reaction order tu dah tak ikut the chemical equation. So that's why the information has to be given to you. So what's the other implication? Maksudnya in this reaction, for this reaction to occur, untuk 1A to react with 2B, the rate determining step is actually the combination of two atoms of A. Dia kena combine dulu baru dia boleh bertindak balas, okay, dengan B to produce the product which is C. So that's the implication bila dia kata non-elementary rate law. Bila dia kata elementary rate law is actually depending on the mechanisms of the reaction and most importantly the rate determining step. Sebab rate determining step itulah yang we will use to calculate the rate law. Right. So we are done on the rate law. We are done on the reaction order. We are never done on the rate law. We are done on the reaction order. Okay, ini we understand apa tu first order, apa tu second order, what is a zero order, how to write the rate law, dia elementary ke non-elementary rate law, and how do we write the rate law. Okay, now we go to the next part. K. Okay, now kita nak cari pula and we want to understand what is actually K. Okay, so we actually, this part is to understand on the unit of K. So maybe you kenapa kena tahu unit? Okay, so the unit of K can be used to actually deduce your rate law. So what do I mean by deducing the rate law from the unit of K? Okay, so when you see the rate law, right? So on your left hand side minus RA, on your right hand side ada K, okay, ada CA, ada CB, ada alpha, ada beta. Okay. So I was saying that kalau kita tahu unit K, kita boleh deduce the rate law. Okay. Why? Because on your left hand side, it is minus RA. So I told you minus RA itu adalah rate of reaction. Okay. So rate of reaction itu adalah concentration, dia punya dimension dia adalah, it's basically the concentration of A with time. Okay, so concentration per time dimension dia is always concentration per time on your left hand side. Means unit minus RA itu will never, unit minus RA itu ataupun dimension dia takkan berubah. It's concentration per time. So let's say mole per dm cube minute, kilomole per liter second, so on and so forth. So on the left hand side, unit dimension will not change. Okay. However, if you look on the right hand side, okay, dia punya reaction order dia can change, right? Means alpha and beta, as I told you, can be zero order, first order, second order. So because of this reaction order can change according to the reaction, therefore the unit K pun will change. So when we know how this K unit changes, or the dimension to be exact, apa beza unit dengan dimension? Contohnya dm cube tu unit, dimension dia volume. Unit, let's say the time, the unit second, the dimension is time. Okay, so means if we know the dimension of K, we can actually tahu ataupun we can agak the alpha and beta, we can agak the reaction order, the alpha and beta. So what do I mean by that? Okay, now let's say you have the first one at the top on your right. Let's say it is zero order reaction. So kalau zero order reaction, minus RA equals to K. Okay, sebab katakan CA power 0. Power 0 is 1, right? So dah tak ada dah CA tu. So become minus RA equals to K. Means reaction rate tu sama je dengan reaction rate constant. Okay, so since I told you, dimension for minus RA is concentration per time. Hence, of course lah, dimension for K pun sama. So the K dimension will be concentration per time. So for example, unit dia mole per liter second, kilomole per dm cube hour, or American Engineering Unit, pound mole per feet cube second. So means, katakan if you see why this is important is katakanlah you look from literature. The literature says, okay, the value of K is 4 mole per dm cube second. Okay, so you know mole per dm cube tu concentration, second to time. So dimension K tu concentration per time. So you know you can deduce rate law dia adalah zero order with respect to A or zero order with respect to B. Tak ada, tak kisah pun apa-apa. It's still rate law dia masih minus RA equals to K. So you can deduce this is a zero order reaction just by looking at the unit. Okay, now next, let's say first order reaction. Okay, so as we told you, kalau kita ada dua reactant, okay, kalau kita satu reactant tak apa, kita terus tahu minus RA equals to KCA. However, let's say you have two reactant. So kalau two reactant, kalau you say first order, it has two possibility. Minus RA equals to KCA or minus RA equals to KCB. Either way pun is first order with respect to the compound, right? Either A or B. Okay. So how do we guess the unit? Okay. So let's say katakan kita letak on the left hand side concentration per time. Okay. Sebab minus RA, as I told you, dimension dia masih sama, concentration per time. On your right, okay, K is the dimension we want to know. Okay, itu adalah unit ataupun dimension yang kita nak tahu. CA or CB, regardless either one, dia punya dimension dia masih concentration. CA and CB is concentration, right? So when I do this, I will get the dimension of K as 1 per time. So katakan per second, per hour, per minute. So if you still remember mathematics, kita boleh cancel kan concentration on your right. You bring to the left, you can cancel the concentration. You are left with 1 per time. So as I told you, katakan you look from literature, you tengok, dia beritahu the value of K is 4 per second, katakan. So when you look 4 per second, you look at your reaction. Katakan reaction tu only one reactant. Okay, so kamu tahu dalam reaction tu ada satu reactant. Dia punya K is first order punya K punya unit. So you can definitely terus deduce minus RA sama dengan KCA. Tapi as I told you, kalau ada dua reactant, you cannot really pinpoint sebab as I told you, kalau first order ada dua reactant, it can be either towards A, first order with respect to A, or first order with respect to B. So dia boleh jadi minus RA sama dengan KCA. Dia boleh jadi juga minus RA sama dengan KCB. So although you can deduce is first order reaction, but when you have two reactant, you can no longer pinpoint exactly first order with respect to what reactant. Okay, unless you do the experiment or you read more on the literature to find out exactly. Tapi deduce tu kamu dah boleh agak dia first order reaction. Okay, what about katakan dia adalah second order reaction. Okay, so kalau second order reaction, okay, kita tengok dulu apakah dia punya dimension. So on your left hand side minus RA still concentration per time, dia tak change. On your right hand side, K, the dimension that we want to know, multiply with concentration power of 2. Sebab reaction tu second order kan, second order concentration power of 2. So you will get finally the dimension for K is 1 per concentration time ataupun unit dia can be liter per mole hour. dN cube per kilomole second. Feet cube per pound mole second. Okay, so from this unit, you can deduce that it is second order reaction. Tetapi then depends juga kepada the reaction. If you have only one reactant, katakan reactant A only, and you see the dimension of K is second order, you can terus dah tulislah, dia mesti minus RA equals to KCA power of 2. Kalau satu reactant je nanti tak balas, then dia kata second order, confirm lah minus RA equals to KCA square. Tetapi as I told you, kalau ada dua reactant, dia dah tak straightforward. So if you have A and B reactant, and kamu tengok literature tu kata dimension for the K ni, unit dia adalah second order. Dia ada 3 possibility, which is first possibility, minus RA equals to KCA power of 2. Means second order with respect to A, zero order with respect to B. Masih second order. Second possibility, minus RA equals to KCB power of 2. And means dia adalah second order with respect to B, zero order with respect to A. Pun masih second order. Or third possibility, minus RA equals to KCACB. Meaning first order with respect to A and first order with respect to B. Overall order still second order. So unit K dia masih sama unit. Tetapi order dia dah berlainan. So when you have two reactant, although you can already deduce dia second order, tetapi to pinpoint the order specifically to the reactant is no longer straightforward. Kamu dah tak boleh straight deduce. Tetapi you can use the knowledge to know dia adalah tindak balas second order. Okay, so as I told you, reaction order ni tak depends. Elementary, non-elementary. Kalau elementary tak apa, terus tengok chemical equation, dah tahu reaction order dia. Meaning dalam the real reaction, it follows the chemical equation. But kalau non-elementary rate law, dia dah tak ikut persamaan kimia. As I told you, sebab reaction tu bukan hanya only one pathway, dia kena melalui few pathway or we call it mechanism, and only satu pathway atau satu step satu saja yang kita panggil sebagai rate determining step, and that pathway step specific itu yang kita akan calculate the rate law. That's why dia punya order tu dah tak ikut the stoichiometric coefficient. Okay, so that's the knowledge that we learn to deduce using the unit. Okay, so next part is now we will learn about again on K. Tetapi sekarang we learn on how to calculate K. Okay, we talk a lot about K, reaction rate constant. Tetapi actually what is K and how do we calculate K? Okay, so reaction rate constant, or also known as specific reaction rate. So this K you can call as reaction rate constant, or you can also call it as specific reaction rate, okay, is dependent on temperature. So one thing that you have to really understand, reaction rate constant is highly dependent on temperature, meaning if you change your temperature, value K akan berubah. Okay, what is the implication? Sebab tu, when you have a reactor, you want to change any of the property, especially temperature, and then later you will learn pressure. Kalau you change any of this one parameter, you will actually already disturb the reactor performance. Kenapa? Sebab kalau you change temperature, kalau you tengok rate law ni, if you change temperature, you will change K. Nanti kita akan tengok the correlation between K and temperature. Let's say in the reaction, dalam reactor tu, let's say you want to increase the temperature, okay, and you do not think about the implication, okay, dia akan ada implication terhadap the reactor performance, because when I change K, I change temperature, value of K change. Value of K change, minus RA will definitely change. Kalau minus RA berubah, kalau you remember, in our design equation ada minus RA. So definitely when you change temperature, I change K, I change minus RA, any changes in my minus RA, my reactor performance tu dah akan berubah. Okay, so means, let's say your reactor performance, you want to, you thought of maybe, okay, katakanlah your heater rosak ke, something ke, you think that, okay, tak apa, slight temperature change will not affect. Even a slight temperature change will affect your reactor performance. That's why I think in industry, process control of reactors are very, very important to minimize or completely erase all these changes of temperature, all these changes of pressure, because reactions are highly, highly sensitive to the change of parameters. Okay, so then that's why if you realize why sometimes reaction dia akan increase temperature, why increasing temperature has the tendency to improve the reaction, is because when you increase temperature, value K will definitely increase as well. Nanti I will teach you the equation. You can see a direct correlation. Temperature naik, K naik. So kalau you nampak, K naik, minus RA naik. Minus RA itu kan rate of reaction. So you are trying to increase the rate of reaction. A higher rate reaction means more A will react with time. So kalau lebih banyak A bertindak balas dengan masa, lebih banyak produk yang you dapat. So that's why certain reaction, they want to go to higher temperature is because they want to increase the minus RA, increase the K, increase minus RA, increase actually the product. However, you cannot simply naik juga. You cannot just, okay, nak naik lagi tinggi lagi bagus. Not necessarily, because if you increase certain temperature, you may disrupt the reaction. Meaning, dia boleh, sekarang bila kamu naikkan suhu, you might actually introduce other types of reaction ataupun ada mechanism atau ada pathway yang mungkin boleh berlaku that cause you will not get the product. For example, oxidation dengan combustion. Oxidation and combustion both actually uses oxygen gas. Oxidation for oxygen gas, combustion, you know, burning is definitely oxygen gas. Okay, so normally oxidation occurs at a quite moderate temperature. I think below 300, below 200 oxidation. Okay, so maybe you think, okay, if I use about 200-300, I tak dapat produk yang banyak daripada oxidation, why not I increase? However, when you increase the temperature to certain level, reaction tu sekarang akan jadi combustion. So kalau combustion, you dah dapat produk yang berlainan. So kalau combustion, normally you will get back gas lah. So if you're combusting, let's say, carbon compounds, you get CO2, you get methane. You no longer get the chemicals or the product that you want. So although temperature helps in the reaction, but you must remember that dia ada juga tendensi untuk menyebabkan jenis tindak balas yang lain pun boleh berlaku, because you know reaction involve chemical bonds ataupun involve breakage or combination of chemical bonds. You naik sikit suhu, certain type of mechanism pun boleh berlaku. So you might not get the product that you want although you increase the temperature. Okay, so to prevent this from happening, okay, so one of the alternative instead of increasing temperature is they use catalyst. So bila they guna catalyst is why a lot of actually the reactions or reactors in the industry will use catalyst. Sebab catalyst has the tendency untuk increase actually the reaction rate constant without the risk of having other reaction taking place. That's why the study of catalyst is a very complex study, and memang industrial, when they're talking about reactors, the study are mostly on adopting catalyst and improving the catalyst performance. Sebab catalytic reaction has high specificity, means dia akan specific untuk increase the rate of your specific reaction and less tendency untuk menyebabkan tindak balas lain boleh berlaku. Okay, so that's one way. You use catalyst, you can also kacau, you can increase the K naik, minus RA pun naik, so rate of reaction increase. Another way, if you are using gas, if your reactants or your reactants are gas, you can also play with the pressure. So dia macam temperature jugalah, certain amount of pressure will help to increase the reaction rate constant and will help to increase the minus RE. Or another way is, if you have liquid, you play with the polarity of the liquid. So ionic strength lah, so you play with the polarity of the liquid. So this also boleh increase the K. So increase K, increase minus RA, or in a simpler word, minus RA lebih baguslah your product amount, ataupun you will get more product from it. So there are few ways that you can manipulate the value of K. So the value of K itu bukan just a number, but it's a way for you to then look how are you going to able to improve the performance of your reactor. Okay, now we go towards understanding the correlation between K and temperature. Okay, sebab just now I told you temperature, the increase of temperature will increase K. So of course a statement cannot just be a statement. In engineering, it has to be in terms of an equation to relate. So this relationship is given by what we call as Arrhenius equation. So Arrhenius equation states that K, the reaction rate constant, equals to A. So I will explain to you apa tu A. So A exponential minus EA per RT. So A exponential power minus EA per RT. So what does it mean? Okay, so first A. So A is your pre-exponential factor, or we also call it frequency factor. Either one pun boleh masuk, it still refers to A. So either we call it pre-exponential factor or we call it frequency factor. Okay, next. Exponent, you know lah, exponential, right? In bracket, minus, negative. The negative is always there, don't forget. EA. So EA is activation energy. I will explain later what's activation energy. R is gas constant. T is temperature. Kan dia kata, dia kan correlate K dengan T. So you can see from the equation, the increase of temperature will definitely increase your value of K. Okay, then let me touch on the gas constant first. Okay, so kalau sebelum ni, I'm sure you have encountered gas constant before, R kan? You have a lot of gas constant value depending on the unit. Okay, so kenapa kita ada banyak value gas constant is because depending on the unit of the R that you want to use. Okay, in the case of energy, okay, energy calculation, or to be more exact, in the case of Arrhenius equation calculation, there's only two gas constant that you will use. Either 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. Okay, kenapa ni dua value ni? Because the value of EA tu energy, which I will explain later. So energy ni normally dalam bentuk, EA ni dah dalam bentuk joule per mole or calorie per mole. So when your EA is in the form of joule per mole, calorie per mole, that's why your gas constant is either these two, either 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. Either way pun unit temperature dia adalah Kelvin. Right. Okay. So next I will go is on the activation energy. So what does apa tu activation energy? Okay. So activation energy in a simpler word to explain is the minimum energy needed by your reacting molecule before the reaction can take place. Okay, kenapa they need this minimum energy is because you know in reaction, for it to occur, dia mesti ada certain bonds that kena break and certain bonds will be formed. Okay, contohnya lah macam kes A and B. Kalau dia nak combine untuk bertindak balas, the bond has to be formed between A and B. So, in order for the formation of bonds and the breakage of bonds, these molecules have to have enough energy, or we call it the minimum amount of energy. So, this minimum amount of energy is what we call as activation energy. Okay, contohnya katakan, let's say in your reactant, okay, let's say the reaction minimum activation energy dia adalah 10 kilojoule per mole. Meaning, as long as your molecules don't have enough 10 kilojoule per mole of energy, the reaction will not occur. Sebab tu sometimes you realize in reaction, why do we heat it up? Kenapa kita panaskan certain reaction? Because when you heat up the molecules, you are providing energy. Heat tu kan in form of energy. So when you heat up, you panaskan, you are providing energy to the molecules with the hope that eventually dia akan sampai enough energy baru tindak balas tu boleh berlaku. So if you have reacting molecule, they don't have enough energy, the reaction will never take place. Okay, so again, the reaction will never take place unless you provide, ataupun unless the molecule have enough energy that is sufficient, which is what we call activation energy, only the reaction can take place. So of course, okay, that's why activation energy is one of the way for you to compare or to know which reaction is better. Maksud dia, katakan, let's say in your case now, your plant is producing this chemical C, katakan, right? Okay. So let's say all this while you have been producing this chemical C through a reaction. Let's say we call it reaction 1. Okay, so from this reaction 1, you can actually measure activation energy dia. You can know the EA. So let's say reaction 1, which you have been using all this while, dia punya activation energy dia, let's say 10 kilojoule per mole. Okay, so kamu tahu reaction 1, 10 kilojoule per mole untuk this activation energy. Okay, let's say one day a chemist came and said that I have an alternative reaction untuk menghasilkan produk yang sama. Okay, so how do we know whether reaction kedua ni lebih baik atau tidak? One of the way, compare activation energy. Sebab dia punya theoretically ataupun logically, kalau reaction tu ada activation energy, the reaction with a lower activation energy is a better reaction. Sebab dia hanya perlukan tenaga yang lebih kurang dia dah boleh, tindak balas tu dah boleh berlaku. Or in simpler word, if you are given either to climb a Mount Kinabalu or to climb, let's say, Everest, of course, naturally it's easier to climb Mount Kinabalu because Mount Kinabalu is a lower peak compared to Everest. So, reaction pun sama. Kalau reaction tu ada activity energy lebih rendah, it's easier to conduct that reaction in comparison to another reaction that has a higher activation energy. Sebab kalau high activation energy means kamu kena provide dulu energy tu, baru tindak balas tu boleh berlaku. Okay, so let's say the chemist says my reaction 2 is a better reaction. So you can compare activation energy. Kalau reaction kedua tu has a lower activation energy, then yes, technically it is a better reaction because of the lower activation energy. However, it cannot be the only consideration. Kenapa? Sebab maybe walaupun reaction 2 tu activation energy adalah lebih rendah, tetapi mungkin the reactants are expensive. Okay, maybe they need a very expensive reactant, or maybe the reaction 2 tu maybe guna catalyst, also possible, but perhaps the uses of catalyst is not so feasible, or maybe the catalyst is expensive, not economical. So again, there is one of the consideration sebab kita boleh banding reaction, tetapi as the only criteria, no, because there are many other criteria you will have to consider before we can really say which reaction is better than the other one. Okay, right. So that's on activation energy. And of course, as I told you before I go further, most of the common reactions, there are people who has already found the activation energy. So kalau macam reaction tu common, you don't actually need to run the experimental work. You can just find from literature. I'm very sure there are someone who has already determined the activation energy for that specific reaction. Sebab you must remember, activation energy ni is specific to the reaction. Meaning, if let's say you use A reacting with B with the same type of reaction, activation energy dia adalah sama. Means if someone wants to run the reaction in Malaysia, wants to run in Singapore, and wants to run in Japan, Indonesia, if you use the same reactant, the same operating condition, the activation energy is still the same. Even if you use different types of reactor pun. Katakan you are using batch. Someone over there uses CSTR or someone over there uses PFR. Asalkan condition sama, raw material sama, you do the calculation for the activation energy is still the same activation energy sebab activation energy is specific to the reaction, not the reactor. Okay, so that's what definition of activation energy. Okay, now next. In this question, this is an example of a question where we try to find K. Okay, so we try to find K using using Arrhenius equation. So they say A and B react to form C with an activation energy of 3 kJ per mole and a pre-exponential factor of 0.5 liter per mole minute. Calculate the reaction rate constant at 70 Celsius. Okay, so from this question, what can we deduce? So first of all, dia kata activation energy 3 kJ per mole. So means EA 3 kJ per mole. Okay, then tetapi why I write here as joule per mole? Sebab remember I told you gas constant dia ada dua saja nilai, right? Ada 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. But since my EA in the form of joule, so of course I will use 8.314. Tetapi 8.314 ni adalah joule per mole Kelvin. So my value originally of my EA was kilojoule. So I have to convert to joule. So kilojoule convert to joule, multiply 1000 sahaja. So meaning let's say contohnya lah 1 km, 1000 meter. So sama. 1 kilojoule, 1000 joule. So kalau 3 kilojoule, 3000 joule. So you just multiply with 1000. Okay. Then A, your pre-exponential factor 0.5. Temperature 70 Celsius. Means kita nak cari K pada 70 Celsius. Okay. So then next. Okay. Using the Arrhenius equation, K equals to A exponential minus EA per RT. Okay. So A, you replace 0.5. EA you replace with 3000, but don't forget dia ada negative sign. So the negative has to be there. Okay, dalam Arrhenius equation tu ada negative. Negative divided by R 8.314 times with temperature. So the temperature 70 plus 273.15. So again because the R value, the unit of temperature is Kelvin. So you have to convert the temperature to Kelvin, right? So 70 Celsius to convert to Kelvin, you just add 273.15, okay? And then you will calculate, you will get the value of the K. So in my notes, I didn't calculate the final answer. Later when you have time, you just calculate and see whether you can do the calculation to obtain the value of your K, right? So done on finding K. Okay, right. So now next part. Okay, for this Arrhenius equation, actually we have the second version of the equation. Just now what you learned was the first version. This is the second version of the equation. So kenapa kita ada second version? Okay, now as I told you before this, okay, K changes with temperature, right? So one way of you finding the value of K was using the Arrhenius yang the one that I taught you, means to find K, A exponential minus EA per RT. Meaning, if you want to find K, you need to know three unknowns. A, pre-exponential factor, activation energy, temperature. Without these three unknowns, I cannot find my K. However, there is another alternative equation, which is actually the second version of the equation, of which you can also find the value of K, but you don't need to know pre-exponential factor. On the other hand, you need to know another two things. What do I mean? Okay, second version ni katakan, for example, you already know the value of K at the first temperature, T1. Katakan you know K at 70 Celsius, katakan 0.5. Means I know at 70 Celsius, my K is 0.5. Okay. Let's say now, you want to change the temperature. Let's say now I want to change to 100 Celsius. So what will my value of K will be? Kan, because I told you K change with temperature, right? So if I say I know K at 70 Celsius, 0.5, now I want to know K at the new temperature at 100 Celsius. So for in this case, meaning I know K1, T1, I want to find K2 at T2, you can use this second version of the equation just by knowing EA, which they tell you the correlation K at T2 ataupun K at your new temperature equals to K at your old temperature exponential in bracket EA per R. In bracket again, 1 per T1 minus 1 per T2. Tutup bracket. That's why I told you, remember, kalau nak cari K2, asalkan you know K1, T1, you know the new temperature, you know EA. R kita dah tahulah, gas constant. So this second version is basically when you want to find new K at new temperature with the prior knowledge of K1, T1. Means tahu K1, tahu T1. Kita ada T2, kita nak cari K2. Okay, so how do we do this? Okay, so this is one example. Let us try one example. Okay, contoh dalam example ni, given a reaction rate constant 1.5 at 80 Celsius with activation energy 5 kilocalorie per mole. So the question says, pada suhu 80, T1 80 Celsius, K1 is 1.5. So K1 1.5, T1 80 Celsius, EA 5 kilocalorie per mole. Okay, so itu EA. They want us to find K, reaction rate constant, at 120 Celsius. So T2 dah 120, K1 0.5, T1 80, T2 120, berapa K2? Okay, so in this kind of question, we can use the second version. Okay, perhaps you ask, kenapa tak boleh guna version pertama? Version pertama kita kena tahu pre-exponential factor. You realize in this question, kita tak tahu pre-exponential factor. If we know pre-exponential factor, yes, we can use the original equation. Tetapi we don't have the pre-exponential factor, so we use the second version of the equation. Okay, so K at 120, the new temperature, K at the new temperature equals to K at 80, K at the old temperature exponential. Untuk the second version ni dah tak ada negatif. That's why you see the second version of the equation, EA tu dah tak ada negatif. Okay, kenapa tak ada negatif? Kalau kamu perasan technically, sebab dalam bracket ni, dia dah menjadi 1 per T1 tolak minus 1 per T2. Technically, dia kalau you, actually this is mathematics. So, you can actually do the derivation. By right, dia adalah minus EA per R dalam bracket 1 per T2 minus 1 per T1 by right. Sebab tu negatif tu dia darabkan dalam kurungan, dia multiply the negative in the bracket. That's why dia jadi 1 per T1 minus 1 per T2. And the negative sign is no longer there. Okay, by right. That's why it become that way. Okay, so come back to the question. So you replace the K at the old temperature 1.5 exponential EA again, sebab in this example EA is in the form of kilocalorie per mole, but R kita akan guna 1.987 calorie per mole Kelvin because of my R tu calorie per mole Kelvin. So my EA pun I have to change to calorie per mole instead of kilocalorie per mole. So 5 kilocalorie per mole is actually equals to 5,000 calorie per mole. Okay, so multiply, divide by R in bracket 1 per T1. Okay, 1 per original temperature, tetapi again because my R value unit temperature dia Kelvin. So my temperature Celsius convert to Kelvin. That's why it become 80 plus 273.15. So 1 per T1 minus 1 per T2. So the T2 120 Celsius plus with the Kelvin plus with 273.15. Okay, the second temperature. So you solve this, you will get the K for the new temperature. So again, I didn't solve the final answer. Later when you have time, you can try to solve the final answer to obtain your value of K. With the understanding, as I told you, K will increase with temperature. Maksudnya dalam case ni, if 80 Celsius, K is 1.5. At 120, K dia definitely bigger than 1.5, more than 1.5. So if you get your K less than 1.5, you have to recheck the equation sebab dia tak boleh. Dia mesti K increases with temperature. So that's one way for you to check your calculation lah. If you get K to lesser, you can check because that means there's something not right about the calculation. Okay. So next one, okay, is to understand how do we get EA. So remember I told you EA is obtained from experiment. Okay, so by right in your lab report, you're supposed to do this. Okay, in your experiment by right, you have to do this. You have to do your experiment. Okay, then you will use the experimental result to get your EA and as well as your E. Okay, so how do we do this? Right, so how do we do this is that, okay, from your experiment, by right, experiment 1, experiment 2, experiment 3 pun sama, you will run the experiment at different temperature. Okay, so for example, you do experiment at temperature 30, 40, 50, 60, 70, katakanlah. Okay, so let's say you look at your left hand side daripada graph tu, okay. For each experiment, you can calculate the value of K. Okay, akan ada specific formula. Okay, dalam lab manual tu ada, dia akan tunjuk how you can calculate the specific K for each of the temperature. Meaning, at 30 Celsius ada K. At 40 Celsius ada K. K yang berlainan lah sebab K kan berubah dengan suhu. So, you imagine I run at T1, I got K1. T2, K2. T3, K3. T4, K4, so on and so forth. So, you imagine that's what you have right now from the experiment. Yang graph yang sebelah kiri. Okay, now, kalau you perasan, okay, from the equation, Arrhenius equation yang original, K equals to A exponential minus EA per RT. Meaning, katakan you plot K, reaction rate constant versus temperature, you will get not a straight line. Okay, you will not get, basically you get a plot, but the plot will not be a straight line. So, bayangkan you kan ada for you to plot a graph, you need to have data for every point tu kena data part CY, part CX. So you have the K1, T1, K2, T2 tu semua, you plot the graph. Okay, maksudnya titik pertama K1, T1, titik kedua K2, T2, so on and so forth. You will have a plot tapi dia bukan straight line because the Arrhenius equation originally is not a linear equation. So kalau bukan linear equation, definitely plot kamu will not be a linear line. Okay, so tak boleh solve lah, susah lah kamu nak solve. So what we do is, we will linearize the equation. Sebab kalau saya linearkan equation and saya plot graph itu, saya akan dapat straight line. Okay, tapi nak linearize equation tu bukan sembarangan. Okay, you have to do it in a proper mathematics way. So how do we do it is that by taking the natural logarithm on left and right. Means yang persamaan original Arrhenius tu. So I will ln on the left, I will ln on the right. Okay. So if I ln on the left, dia jadi ln K. Okay. So part kiri ln K. Okay. What about part kanan pula? So part kanan, the first is A. So A I will ln kan. So become ln A as you see on your right hand side. Okay. What about yang exponential minus EA per RT? Okay. So part exponential minus EA per RT, when you ln kan, exponent tu dah hilang. Okay, mathematics. Exponent, bila kamu ln kan exponent, the exponent is no longer there. What happens? The power tu akan turun bawah. So, dia menjadi minus EA per RT. So, now the equation become ln K equals to ln A minus EA per RT. Tengok dia dah linear equation. Tetapi, tadi kita kata, why kita nak linearkan equation tu? Kita nak plot graph, right? Kita nak cari EA dan R, right? Okay, so Kalau kita nak plot graph, equation tu must be in the form of y equals to mx plus c. Means y tu data paksi y, the x is the data for paksi x, the m is the slope, the c is your y-intercept. Okay, so kita kena decide apa akan menjadi data paksi y, what will be the data for paksi x. So data ni you cannot sembarangan ambil because you must remember apa original data that you have. Data jenis kita ada adalah K dan T. Hence, my ln K can become my Y. Sebab saya ada K, means nilai K yang tadi yang K1, K2, K3, K4. If I lnkan the K, that will be my Y axis data. So now I have ln K1, ln K2, ln K3, ln K4. Means K yang saya dapat tadi kan, K1 katakan 4. I lnkan 4, that will be my ln K1. Katakan K2 5. So I lnkan 5, I dapat the ln K2 punya data. Done. So naturally on my x-axis, apa lagi saya tahu? Temperature. Because I know K1 and T1 for experiment, right? Tetapi I can no longer just put temperature. Sebab dalam equation dia become 1 per temperature. Kan? Sebab equation asal dia kan ln A minus EA per RT. So means my x-axis data is now 1 per temperature. So tadi yang T1, katakan T1 50 Celsius, now menjadi 1 per 50 Celsius, 1 per T1. My T2, let's say 100 Celsius, now become 1 per T2. I jadikan 1 per 100, I dapat data for T2. So tadi K1 T1, now jadi ln K1 1 per T1. K2 T2 jadi ln K2 1 per T2. 2 point. So on and so forth. So you have 4 points tadi kan? Okay, so we plot the point. So when you plot the point, you will definitely get a straight line. Sebab equation dia dah linear. Your plot, bila kamu plot, you will get a straight line. So then, apakah implication dia? Because kita kata kita nak cari EA dan A, kita nak cari EA dan A kan? Okay. So you look back the equation. Kalau ln K is Y, 1 per temperature is my X, naturally my gradient minus EA per R ni adalah gradient saya or my slope. Meaning I plot the graph, I know the slope. Kalau you guna Excel, Excel will find for you the slope. The slope is equal to my minus EA per R. So you plot the graph, let's say you get the gradient. Katakan gradient dia adalah 5. So means minus EA equals to 5. R tu kan gas constant. Kita dah tahu gas constant kan depends lah. Kalau you nak EA in the form of calorie per mole, you multiply 1.987. You use 1.987. If you want your EA in the form of joule per mole, you multiply 8.3144. Either way, you will get your EA. Sebab minus EA sama dengan gradient. And when you plot the graph, definitely gradient dia, kecurunan dia adalah kecurunan negatif for sure. Okay, sebab tu baru nilai negatif ni akan musnah. Okay, so you will get your EA. Slope, okay, slope sama dengan minus EA per R. Slope darab dengan R, you get your EA. Done. What about my pre-exponential factor? So if you look from the equation at the bottom, ln A is my y-intercept. Because dia akan jadi y equals to mx plus c. So ln A is my y-intercept. So you look at your plot, you find your y-intercept. If you're using Excel, you can find for your Excel your y-intercept. Your y-intercept is your ln A. So katakan your y-intercept adalah 5. So ln A sama dengan 5. So A sama dengan exponential 5. You know right? Mathematics kan? Kalau ln A sama dengan 5, A sama dengan exponential 5. So you press your calculator, exponential 5, or you can find from any other ways, you will get your A. So that's how actually we determine A and EA from the Arrhenius equation by plotting a graph. Okay, so buat eksperimen, cari K1, T1, K2, T2, so on and so forth. Plot, dan kita linearize, plot graph ln K versus 1 per temperature. You will get your EA, you will get your A. Okay, so that's how we actually obtain from experiment. Okay, So there's another one more question, tapi this question I would like you to attempt by yourself when you have extra time, because for this question I provide the final answer and everything just to test your understanding. You may try to do this later. Okay. But before I go to the next part, okay, I will take a little bit of break, about 5-minute break. I will come back about 10:20. So maybe if you have time, you can also take a break, or if you have time, you can just look at this question. So I will come back in about 5 minutes time. Okay, saya switch off kamera dan mic kejap. Saya will come back in 10:20.
Oke, dokter.
Okay, so we'll continue to the next part. All right, so we are basically done on the rate law. Okay, so bukan belum habis lagi rate law, sorry. So we have done on certain part of the rate law. Okay, so first part we done on the reaction order. Kita dah faham pasal reaction order. So ada elementary, non-elementary. Kalau elementary, you look at the stoichiometric coefficient, dia sama dengan stoichiometric coefficient. Non-elementary information has to be provided. So that's on reaction order. Second, we find how to get K. So kita tahu macam mana kita dapat K from equation, how to calculate K if you are given prior knowledge of the value of K at other temperature. We learn how to get K from experimental work. So that's two. Third one is that now dalam rate law ada CA dan CB. Okay, remember in the rate law, reaction order, the reaction order is towards the concentration of your reactant. So we have to now find how do we dapatkan, how do we obtain the CA and CB. Okay, so the concentration is not straightforward sebab in the real application, we don't normally measure the outlet concentration sebab CA-CB tu outlet concentration of A and B. So how do we determine this concentration of A and B? Okay. To determine this concentration, we will do using what we call as stoichiometric table. We will use stoichiometric table to obtain CA and CB. Okay, so what is this stoichiometric table? Stoichiometric table ni basically, as I told you tadi, is actually mass balance. But this mass balance is for reactive process. Memanglah sebab we are doing it on a reaction. So if you learn before in mass balance, we've got two types of mass balance, right? We got mass balance for non-reactive and reactive. Atau maksudnya kalau your equipment has no reaction, just in equals to out. For example, separator. For example, if you are doing on distillation column, okay, it's just untuk separate saja, dia tak ada sebarang tindak balas. That is what we call as non-reactive. On the other hand, if your equipment, your process unit has reaction, example, reactor, furnace, burner, something like that, yang ada tindak balas, we call it reactive. Okay, reactive process. Reactive process pun, you pernah belajar dalam mass balance, you can use either two method, extent of reaction method or atomic balance. Either way pun kamu boleh guna. Okay, so today, we learn another way, which is by using a table. Just using a table, kita pun boleh juga cari mass dia. Mass balance ni means how much in, how much out. In the form of a table, and this table has certain formula. Okay, so when I teach you the table, it can be a bit confusing sebab table tu ada formula dia. Okay, and when I teach you, it's in the form of symbol. So jadi pening lah sebab ada symbol. However, later, when you replace with number, so bila kita ada number, table tu menjadi senang sebab kita faham number tu easier than in comparison when we put in symbol. Okay, so that's one thing. Okay, so let's understanding on a stoichiometric table. However, stoichiometric table ni, dia ada two types of table. Okay, konsep dia sama sebenarnya. Okay, tetapi why we have two different table is because we have to do it differently. Either you're doing for batch system or flow system. Okay, so as you know lah, kalau batch system, batch reactor. Kalau flow system, CSTR, PFR. Okay, then apa beza dia? Okay, in terms of formula tu sebenarnya later you will see is about the same. Beza dia adalah if batch reactor, I will calculate in terms of number of moles, N. So kita kena kira, kita kena buat balance tu berdasarkan number of moles ataupun N. Or to be more exact adalah with the knowledge of Na. Apa tu Na? N number of moles, A compound A, not is times 0, means initial number moles of A, Na. Okay, so kalau tak tahu Na, kita tak boleh buat table tu. So means balance kita berdasarkan Na, which I will explain to you later aku masuk dia. Okay, beza dia dengan flow reactors. Kalau flow reactors in terms of molar flow rate, mole per time. So kalau batch, mole. Kalau flow, mole per time. So akan menjadi FA0. So maksudnya mole per time, initial moles or initial molar flow rate of A. So tak tahu FA0, you cannot do the table. That's the only difference. Cara pengiraan tu berlainan. Satu guna mole, satu guna molar flow rate. Tetapi konsep pemahaman, the understanding of it is basically about the same. However, sebab kita ada dua cara pengiraan yang berlainan, so the table tu akan jadi dua table yang berlainan lah. So I will explain to you the table for batch, the table for flow. Okay, but if you realise, I told you that the table is, kita nak belajar ni sebab kita nak cari CACB. So apa berkaitan dia? Sebab I talk about NA0, FA0. Okay, apa berkaitannya dengan CACB, right? Okay, so later from the table, you will use the information from the table untuk cari CA, untuk cari CB. You can also find CC. Katakan you ada product, right? CACB reactant. Let's say you want to find concentration of product. Pun boleh by using this table. That's why we have table. The table will help us to elucidate or determine the concentration of A, concentration of B, so on and so forth. Okay, which is what I'm going to show now, right? So, kita cakap in general dulu, how the table looks like. Okay, so the table kan? Okay, so the table will have column, will have rows. Okay, first column. Okay, you will have 5 different column. Kenapa 5 column? It's because the first column is for species. Okay, so contohnya, let's say in your reaction, dalam contoh ni, reaction saya, species saya A, B, C dan D. So, kamu akan ada A, B, C and D. Setiap satu spesies tu, each compound, it will have its own row. Baris dia tersendiri. So compound A is own baris, row. Compound B, compound C, compound D. Meaning compounds in the reaction. And plus, if you have any other compounds in the system, although they might not involved in the reaction, dia mungkin tak ada dalam persamaan kimia, tapi dia ada dalam sistem, or we call it as inert or even impurities. Kalau dia ada dalam sistem, dia harus ada row dia sendiri dalam table tu. So let's say I have inert, we call it inert, right? So we have one row for the inert. Okay, so example lah, okay, contoh yang senang. As I told you, katakan you want to do combustion, okay. So combustion normally is oxygen gas. You will react with oxygen gas. But as most of the time, we don't use pure oxygen because it's definitely not economically feasible to use pure oxygen. You will use air. So kalau air, definitely you will have nitrogen gas. Okay, so although the nitrogen gas is not involved in the combustion, but nitrogen gas is in the system, in the reactor, it will have its own row. Okay, so katakan nitrogen gas tu maknanya spesies dia N2 lah. Okay, sebab dalam kes ni, in this table, saya guna ABCD. Sebab tu spesies dia ABCD. Tapi if you use real compound, for example, N2, O2, NH3, so on and so forth, the species is referring to the real chemical compound itself. So NH3, N2, H2, O2, let's see. Okay, so that's for the species. Next, symbol. So after this, we will convert this real chemical compound into symbol. A, B, C, and D. So for example, let's say the reaction is ammonia to form ammonia, N2 with H2 to form NH3. So you will put species N2, symbol A, H2, symbol B, NH3, symbol C. So if your system doesn't have any other compound, tak ada sebarang inert, hence the row inert tu tak payah ada lah. So it depends on your system. Inert tu depends on your system. You have any other compound as inert, you put the row. If tak ada, you tak letak. So kenapa kita kena letak? Sebab kita kan nak buat mass balance. So although the compound is not involved in the reaction, it has its own mass. So kita kena kira mass tu. So that's why regardless dia involved atau tidak involved, it must be considered in the stoichiometric table. Okay, so that's the second column. Third column, initial amount. So mass balance kan in dan out, right? So initial is to refer to the in. So kalau batch, it will be initial moles lah, molar. Kalau flow, initial molar flow rate. So you will know the initial moles of A, initial moles of B, initial moles of C, initial moles of D, inert. then total initial mole. So I know now my total in of the mole. So example katakan initial A 5 mole, initial B 10 mole, let's see. Katakan C and D produk, tak ada initial mole, katakan tak ada inert. So total mole 5 tambah 4 mole, 9 mole. So total mole yang masuk 9 mole, which come from A 5 mole, B 4 mole, let's see. Okay, next column, change. Change is to address how much each of the compound will change during the reaction. So naturally kalau reactant dia will decrease. Dia akan turun sebab dia consume. So bilangan mole dia akan berkurangan. So product naturally dia akan produce, right? So bilangan mole product ni will increase. So positive for the product, negative for the reactant. Later I will explain to you. So we address berapa banyak bilangan mole ni akan bertambah atau berkurang during the reaction. Then last, remaining. So remaining is to address the out. So sekarang berapa bilangan mole yang tinggal untuk A, untuk B, untuk C, untuk D dan untuk inert. Berapa bilangan mole yang tinggal after the reaction has taken place. So it become total out. So initial total in, remaining the total out. So you know the initial for A, remaining for B, remaining for A. So for B, initial remaining. So you tahu in out A, in out B, in out C, in out D, and ultimately total in, total out for all the compounds. So that's why we do in the stoichiometric table. Okay. However, table dia ada, as I told you, dia tak straightforward sebab dia ada formula untuk kita to determine these moles. Okay, so I start first with batch reactor. Okay, I start first by doing it for batch reactor. Okay, so kita go the first row initial. Okay, so let's say initial ni, okay, as I told you kalau batch mesti dalam bentuk N kan, bilangan mole. Okay, so let us learn how do we calculate this number. Okay, so first of all for species A, initial mole dia Na0 lah. So contohnya katakan in the question say initially there's 5 mole of A. So Na0 sama dengan 5. So right now bila tengok simbol memang pening. Tetapi when you replace with number it become easy. Na0 equals to 5 means bilangan mole asal A in the system is 5. Okay, so A settle. What about B? So kalau A Na0, initial moles of A. Kalau B jadilah NB0, initial moles of B. Okay. So the initial moles of B you can get by knowing theta B and Na0. Ataupun arti kata lain, kalau kita tahu Na0, kita dah boleh buat table ni. Tetapi ada certain simbol yang kita kena tahu juga. So meaning to say, to find NB0 is equal to Na0 multiply with theta B. Okay, Na0 ni you know lah, initial moles of A. Apa ni? Theta B. Okay, so this theta B is something new that you will learn today. So, tambah satu lagi simbol that you have to learn. So, theta B is actually the easiest way to say initial amount of B over initial amount of A. Dia adalah ratio of how much B over A initially. Tapi remember I said amount, how much. Macam mana kita nak quantify how much ni kan? It depends on the question. What is the information given? Because it can be in the form of initial number of moles. Okay, ataupun it can be initial concentration. It can be initial mole fraction. Contohnya, katakan dalam soalan kata, initially there is 50 mole percent A, 50 mole percent B initially. Maksudnya YB0 0.5, YA0 pun 0.5 mole fraction, right? Mole percent tukar fraction. So 50% A, 50% B jadi 0.5, 0.5. So theta B is equal to 0.5 divided by 0.5, 1. Ataupun let's say dia kata initial concentration of A is 5 molar and initial concentration of B is 10 molar. Katakan, dia beritahu initial concentration. Hence, theta B equals to 10 molar bahagi dengan 5 molar. Initial concentration of B divided by initial concentration of E. So, basically, theta B ni adalah dia nak tahu saja ratio ataupun nisbah bilangan B kepada bilangan E. This bilangan, this amount can be concentration, can be mole fraction, can be number of moles. Either way, theta B dia punya nisbah masih sama. So when you get that theta B, you multiply with NA0. So katakanlah, you calculate theta B as 1. So tadi NA0 I kata 5, right? So 5 multiply with theta B 1. So NB0 is also 5. So maksudnya initial moles of A 5 mole, initial mole of B pun 5 mole. Okay, done. Okay, next. C and D. Okay, so C and D, logically, you know, in this example, okay, before I forget kan, dalam example ni, A dan B reactant, C dan D product. So naturally, initial amount A dan B akan ada sebab A dan B adalah your reactant, right? So means at time 0, kita dah ada dua reactant ni. Kita boleh measure berapa bilangan mole. But C and D are product. So pada awal tindak balas, C dan D belum terhasil, belum terbentuk. So NC0 and ND0 will be 0 because they are product and they are not yet formed, okay, at time 0. So NC0 and D0 0 because they are product. Okay. Next, inert. So as I told you, inert if and only if you have inert in your system. So kalau tak ada inert, tak payahlah ada row inert. Tetapi kalau ada inert, okay, you have to also measure bilangan mole inert tu berapa. Contohnya katakan nitrogen gas tu adalah inert. So how much initially that moles of nitrogen gas in your system. So how do we calculate? It become Ni0 equals to Na0 theta I. So Na0 is the initial moles of A and multiply with theta I. Tadi theta B, sekarang theta I. What's the difference? Theta I refers to ratio of initial amount of the inert over A. So kalau theta B, amount B over A. Kalau theta I, amount inert over A. Okay, so contohnya lah, I'll give an example. Let's say in your system, you have A, B and inert. Okay, so let's say dia kata initially mole percent dia, mole percent A 50 mole percent, mole percent B 25 mole percent, mole percent inert pun 25 mole percent. So we got 50, 25, 25, baru 100 kan? So theta B equals to 0.25 divided by 0.5 is half, 1.2, 0.5 jugalah, 0.25 divided by 0.5 is actually 0.25 divided by 0.5 is 0.25, 0.5, still half. Okay, so you get A punya theta B. So kalau theta I, theta inert will be again, berapa percentage, berapa fraction of inert? 0.25, right? So 0.25 divided by 0.5, you get for your theta I. So you can calculate theta B, theta I for the same system. So when you get the theta I, you don't forget multiply dengan Na0 balik. Okay, so tadi kalau theta B multiply dengan Na0, kalau N9 theta I multiply dengan Na0. So contohnya lah, katakanlah we get Na0 5, katakan Na0 5, katakan NB0 4. Okay, katakan Ni0 tu 10. So total initial moles tu NT0 tu 5 plus 4 plus 10, 19. So NT0 19 moles. So NT0 refers to initial total number of moles. So I forget to tell. Row yang paling bawah adalah row total. So total initial. Berapa jumlah bilangan mole yang masuk akan jadi Na0 tambah dengan NB0 tambah NC0, ND0, NI0. So in this example, since A and B adalah reactant, we will have Na0, we will have NB0, NC0, ND0 0, NI0 ada nilai, kita akan tambah juga. So you get your total for the initial. Done. Okay, so that's for the first, third column, initial. Okay, next column, remaining. Okay, change. Remaining pula. I belum sampai change, tapi pergi remaining. Okay, change. So for the column change is to address how much changes of each compound ataupun berapa banyak bilangan mole produk dan reactant akan bertambah atau berkurang in the reaction. What do I mean by that? Okay. Untuk A, okay, for A, okay, how much A akan berkurangan semasa tindak balas is equal to minus Na0X. X is for conversion, NA0 bilangan mol. Why there's a negative? Sebab kan A reactant, A will be consumed. Bilangan mol itu akan berkurangan. So, berapa banyak dia berkurangan? Sebanyak minus NA0 X. Okay, contohnya, let's say you don't understand. Okay, katakan initial A, NA0 is 10 mol. Okay, so katakan berapa banyak dia berkurangan. Let's say X2 adalah 50%. Maknanya X2 0.5. So, kalau 0.5 kali dengan NA0 10 is 5, right? So, it become minus 5. Maknanya, berapa banyak bilangan mol A yang berkurang semasa tindak balas adalah sebanyak negatif 5 mol. Dia akan kurang 10 mol, akan berkurangan sebanyak 5 mol. Sebab tu jadi negatif 5. So means that's 5 yang akan consume in the reaction. So kenapa 5? Sebab conversion dia adalah 50%, 0.5. So 0.5 times 5 times 10 is 5. So that's for the change of A. Okay, what about B? The change for B. Okay. In this example, B is a reactant as well. So of course, bilangan mol B pun akan berkurangan. B will also decrease because B is a reactant. So how much it decrease become negative B per A NA0 X. So B per A ni adalah your stoichiometric coefficient ratio. So you have to look at your chemical equation. So B, let's say B2 1, let's say the A is 1, let's say 1A, 1B reacting, right? So let's say 1A, 1B, maka the B and D per A jadi 1 per 1. So minus 1 per 1, multiply with NA0, multiply with X again. So be very careful about the B and A. Let's say katakan the reaction is 1A reacting with 2B. So the B per A akan jadi 2 over 1. So negative 2 over 1 multiply with NA0 multiply with X. So katakanlah the NA0 is 10, the X is 0.5. Katakan 1, 1. So negative 1 over 1 multiply with 10 multiply with X 0.5. So you will get how much B yang hilang semasa tindak balas berlaku. Okay. Next is C and D. So C and D is product in this example. So kalau C dan D adalah product, naturally for the change, dia akan tambah bilangan mol tu. Means during the reaction, while A and B will decrease the moles, the C and D will increase sebab dia akan terhasil. So how much is the increment of the mole is plus. So jadi plus sebab dia product dia akan bertambah. So plus C per A multiply with NA0 X, and for D plus D per A NA0 X. So C per D, D per A, C per A, D per A. You have to look at the stoichiometric coefficient again. Alright, so for the chemical equation, you know how much of C, how much of D per A, and then don't forget multiply again with NA0 multiply with X. So you get for A, B, C, and D for the change. And lastly, inert. So you know kan, case inert, dia tak akan ada tambah atau kurang in the reaction because inerts are not involved in the reaction. They are in the system, they have the mass, but the mass will not change. The mass will not decrease, the mass will not increase because they are not involved in the reaction. That's why the change for inert is 0. There's no change in the inert amount. Okay, last one is for the remaining. So remaining is actually the easiest one. Yang kena hafal sikit actually initial dengan change. Remaining you don't have to memorize. What do I mean by that? Okay, so again concept dia initial for in, remaining for out. So kalau initial and A0 and B0 and C0 and D0 and I0, remaining and A and B and C and D and I. Sebab not to indicate initial amount, remaining is the outlet lah yang tinggal selepas tindak balas. So how much NA ataupun berapa banyak A yang tinggal after reaction, NA equals to, okay, kamu tengok formula dia panjang tetapi it's the easiest because you just need to combine initial and change. Meaning NA sama dengan you take your initial NA0, you combine with your change negative NA0 X. So it become NA0 minus NA0 X. So change tu tak payah hafal. Ambil initial combine dengan change. Okay, so you get Na equals to Na0 minus Na0 X, or if I want to take out the Na0, letak dalam bracket, it become Na0 in bracket 1 minus X. So later kita akan guna information ni untuk cari concentrations. Now kita dah dapat derive Na in the form of Na0 dan X, which is Na equals to Na0 in bracket 1 minus X. Or we also can know berapa bilangan mol Na yang tinggal after the reaction. Okay, what about B? Okay, so dalam case ni, again, NB equals to, you take your initial Na0 theta B, combine with your change, net minus B per A Na0 X. So that's how you get NB equals to Na0 theta B minus B per A Na0 X. Or you can take out the Na0, dia jadi Na0 in bracket theta B minus B per A X. So now I get for my NB. So sekarang I can express my NB in the form of Na0 in bracket theta B minus B per A X. Okay, so I understand kalau nampak macam simbol ni susah, iris, looks complicated. Tapi later bila kita ganti dengan nombor, sebenarnya dia dah tak jadi susah. Okay, next, C. So C lagi senang lah. C sebab initial tak ada apa-apa. It's only remaining, right? So NC is only change, right? So remaining NC equals to terus change plus C per A Na0 X. Similarly to D. So ND equals to plus D per A Na0 X. Terus equal to the change because initial dia tak ada. For about inert. Inert pun senang sebab inert has initial. Inert got no change. Total inert remaining samalah dengan inert initial. That's why inert remaining Ni equals to inert initial Na0 theta I. So we have already deduced the remaining amount of A, B, C and D in the form of number of moles. And don't forget, we have to calculate the total remaining. So katakanlah remaining A and A is 5. NB, let's say 4. So Na plus NB, 4 plus 5, 9. Let's say NC, 2 plus 2, 11. ND, 1 plus 1, 12. And I katakan 2. So tambah lagi 14. So total remaining 14 means tadi katakan total in 12 mole, total remaining 14 mole. So now you have done another way, you have done the balance for in and out for the whole table. Okay, so now next. Okay, now have to understand a little bit, or might be there's a little bit of confusion sebab for the case of B. Okay, apa maksud saya? Okay, the example that I taught you just now is for the case where we have two reactant. Reactant A, reactant B. So, of course, naturally untuk B akan ada total initial. And for the change, B akan berkurangan sebab B akan consume. However, katakan sekarang case di mana B adalah produk. Misalnya satu reactant. So, kalau satu reactant tu reactant A lah kan. So, produk dia, B tu dah menjadi produk. So, katakan B, katakan dalam case ni, I have one reactant A. I have two product B and C. So, what happens to the table? Okay, yang part lain semua sama except for your B. So, for your B, you can see that the table will have a little bit different because sekarang kamu tengok total initial for B is already 0. Okay. Total change for B sekarang jadi plus B per A and A0 X. Kenapa jadi plus B per A and A0 X? Because in this example, B dah jadi produk. So B got no initial. The change for B akan jadi plus because B is formed. So how much is formed? Plus B per A and A0 X. So what about the remaining? So the remaining become NB equals to the change. So you can see table tu ada slight changes which sometimes student get a bit confused sebab ada certain case ada dua reactant. So kalau dua reactant, kita namakan reactant pertama sebagai A, kita namakan reactant kedua sebagai B. Tetapi katakan kalau tindak balas tu ada satu reactant. So reactant tu akan jadi A kan? So produk dia akan menjadi produk B dan produk C. So untuk case B tu, table tu akan jadi lain. Okay, so the understanding tu penting lah why it becomes like this. Why it has initial? Kenapa tiba-tiba A tak ada initial? Sebab kalau dia ada produk, of course lah dia tak ada initial. Okay, so that's on the table. Right, so but before I continue some more, as I told you, memang table ni nampak susah at first glance sebab dia adalah dalam bentuk simbol, not in the form of number. But once you get number, it becomes easier. Okay, now I go to the next part. Kita nak express concentration. So if you realise, I was telling you kita nak buat table ni sebab dalam read law ada CA, CB. Kita nak cari macam mana kita nak express CA dan CB. So that's why we learn the table. From the table, tadi kita tahu NA and B. Okay, kita pun tahu NC and D. Kita pun tahu NI. So from these 5 remaining number of moles, we can find remaining concentration. CA, CB, CC, CD, CI. So how do we do it? Okay, now, first of all, to express the concentration for batch reactor, okay, for and only batch reactor, to express the concentration, it is the same for liquid and gas. That's the main advantage. Kalau batch reactor ni liquid atau gas, nak express concentration tu adalah sama. Okay, kenapa saya kena beritahu ni? Sebab later kita akan buat untuk flow reactor, PFR, CSTR. So kalau PFR, CSTR, nak express concentration ni dah berlainan untuk liquid dan gas. Tetapi tak apalah, tu that's another day punya story. For today, we want to talk about batch reactor. So for batch reactor, to express this concentration, dia adalah sama untuk liquid dan gas. Why? Because it's based on the assumption of the reactor volume. Okay, reactor volume ni, regardless you use liquid or you use gas, reactor volume will not change. Means reactor volume remain constant. So means your reactor will not expand. Your reactor will not shrink. So reactor volume V equals to V naught, initial volume. Based on this assumption or based on this theory, that's why liquid dengan gas kita express concentration sama. Okay, kenapa dia penting? Okay, sebab nanti bila you belajar when you learn flow reactor, kalau batch kita belajar in terms of volume, kita assume volume. Kalau flow is in terms of volumetric flow rate. Volume, kalau flow, batch volume, kalau flow, volume per time. Untuk volume per time ni, volumetric flow rate ni, dia berlainan. Kalau dia adalah gas, dia adalah liquid, inlet-outlet volumetric flow rate tu sama. Tetapi kalau gas, dia tak sama. Untuk gas, inlet-outlet volumetric flow rate is no longer equal. Because of that understanding, concentration tu kita kena express berlainan. Tapi tu teruntuk flow lah. Tapi untuk batch, sebab kita menggunakan assumption volume, kan kalau flow mesti per time kan, sebab tu volume per time. Kalau batch is just volume. So sebab volume tu takkan berubah, sebab tu liquid atau gas kita express sama. Okay, so how do we express it? Okay, senang je. That's why kita ada table. Okay, so daripada table, kita dah tahu Na equals to Na naught in bracket 1 minus X. We know this from the table. Okay, now kita nak express Ca, right? Okay, nak express Ca, concentration of A. Ingat kan rate law tadi ada Ca kan? Okay, concentration of A is equals to Na per V. Concentration of A, outlet or remaining concentration of A equals to remaining moles of A per volume reactor. Okay, kalau katakan kamu confused part ni, just ingat. Concentration kan mole per volume, betul lah. Na itu kan mole, V itu kan volume, so mole per volume. Okay, so Na tu remaining moles of A. Macam mana kita nak cari? Kita cari daripada table. Table kata Na equals to Na naught in bracket 1 minus X as I derived just now. So we replace Na equals to Na naught in bracket 1 minus X. Okay, then bottom. Bottom originally was outlet reactor volume. Okay, but because we says that volume reactor ni takkan berubah, inlet dengan outlet, initial dengan remaining volume reactor takkan berubah. Macam you got the vessel, volume vessel tu kalau kamu guna 10 liter vessel, 10 liter vessel lah, dia takkan berubah sebelum dan selepas pindah balas. Because of that, I can write the volume, the outlet or the remaining volume of the reactor as V naught. So why do I write as V0? What is the importance of writing V0? Sebab nanti I have NA0 at the top, I have V0 at the bottom. So NA0 per V0 is actually equals to CA0. So now it becomes CA0 in bracket 1 minus X. So now I have expressed the concentration of A, remaining concentration of A as equals to CA0 in bracket 1 minus X. Done. So I dah express sekarang concentration of A. What about concentration of B? So concentration of B, sekarang kamu kena faham. Ada case di mana B adalah reactant atau when B is a product. So kalau B reactant, kamu nak express concentration is different than when the case B is your product. So for example, let's say untuk case di mana B is your reactant, hence CB equals to NB over V. Okay, before I forget, kenapa kita express berlainan? Sebab kamu ingatkan NB tu kan dah berlainan. Kalau B adalah reactant, NB sama dengan Na0 in bracket theta B minus B per AX. Tu katakan kalau B adalah reactant. If B is a product, NB equals to plus B per A Na0X. Because we have this different version of the NB, that's why concentration pun akan jadi lain. Okay, so let us do for the first one. Bila B adalah reactant. So when B adalah reactant, CB equals to NB over volume. Kalau tadi CA equals to NA per volume. Kalau CB equals to NB per volume. Okay, again, mungkin you might ask, kenapa V tu hanya V bukan VA, VB? Sebab V tu refers to the volume of your reactor, not volume of your compound. So that bilangan, maknanya kepekatan A dalam reaktor sama dengan bilangan mol A terhadap volume reactor. If it's concentration of B, moles of B over the reactor volume. So NB, you look at the table, NB is equals to Na0 in bracket theta B minus B per AX. So I replace Na0 in bracket theta B minus B per AX. I divide again with assumption volume reactor does not change, inlet outlet sama. So I replace V with V0. So I don't do this just for nothing. Sebab nanti I can do Na0 per V0, I will get Ca0. So Ca0 in bracket theta B minus B per AX. So now saya dah express CB in the form of Ca0 in bracket theta B minus B per AX. So similarly for CB, I can also express for CB. So I can express for CB when CB is a product. Beza dia adalah kerana sebab remaining moles tu dah berlainan. So express concentration pun dah berlainan lah. So walaupun first step is still the same, concentration of B equals to moles of B over volume. But because B is a product now, so the NB equals to plus B per A Na0X. Divide by volume reactor, instead of outlet, I make it equals to inlet, V0. So B Na0 di atas, V0 di bawah, I divide, I get Ca0. So it become plus B per A Ca0X. So now I express for CB. So I express next one. Let's say kamu nak tahu juga untuk C, D, produk C, produk D and inert. You can also do the same. Okay, guna daripada table. Daripada table saya dah tahu NC, ND, NI. I can express for the concentration. So you will get concentration of C, outlet or remaining concentration of C sama dengan plus C per A Ca0X. Outlet for product D, concentration of D equals to plus D per A Ca0X. And for inert, concentration dia equals to Ca0 theta I. So dia hanya, that's why kita perlukan table sebab kita nak express concentration it, to express the concentration, we need to know this value from the table. Alright, okay. So before we finish for the class today, let's us do one example untuk kita tengok betul-betul kita faham ke tak. Sebab memang when I explain in terms of symbol, memang from previous experience memang it's hard to grasp the concept. But from an example is much easier. Okay, so let us try this example. The formation of ammonia gas, NH3, can result from the reaction of nitrogen gas with hydrogen gas. Okay, so dia kata dia specify reaction dia is between nitrogen gas, hydrogen gas, you get ammonia. Okay, so then you'll be very careful. The reaction is 1 nitrogen gas with 3 hydrogen gas to get 2 ammonia, 2 NH3. Okay, so stoichiometric coefficient tu dah very important for you to notice. Okay, next dia kata isothermal, isobaric, irreversible reaction. So sebelum ni maybe you have heard but you don't really understand the particularity of it. But isothermal to indicate there's no change of temperature. Isobaric to indicate no change of pressure. Irreversible reaction meaning the reaction is forward direction. Means the reaction will go always from nitrogen, hydrogen to produce ammonia. Okay, so far until chapter 3, we only learn this. No change of temperature, no change of pressure, and irreversible. But later on, nanti when we go to chapter 4, you will learn chapter 6, you learn non-isothermal, ada perubahan suhu. In chapter 4, you learn pressure change. And then chapter 4 again, you will learn reversible. Kalau reversible, it goes forward, backwards. Meaning kalau reversible, N2 dengan H2 boleh menghasilkan ammonia. Ammonia boleh backward menghasilkan balik N2 dengan H2. Itu kita akan belajar dalam chapter 4. Okay, so in this case, 3 ni tak applicable, istilah isothermal, isobaric, irreversible. Okay. Initially consists of 60 mole % hydrogen and the balance nitrogen. Okay, what is the significance of this sentence? Okay, dia kata mole percent, you know, right? Mole percent kita boleh tukar kepada mole fraction. Means awal-awal dalam tindak balas tu kita ada hydrogen and nitrogen and dia adalah 60% hydrogen and of course 40% nitrogen lah. Okay, then next kita kena faham pula which one is A, which one is B. Kita nak tahu mana satu YA0, mana satu YB0 kan. Okay, so you look at the reaction. Okay, ataupun another reaction tu kata another way to indicate juga. Saya kena skip satu ayat. Dalam soalan pun kata N2 must be used as the basis of calculation. So dia dua benda yang kamu kena tengok sebenarnya. Okay, tetapi ayat yang paling strong if they give this sentence, N2 used for basis. Maknanya dia kata N2 sebagai asas pengiraan, your basis of calculation, or in other words, N2 is your A. Okay. Another way, katakanlah dia tak cakap which one is to be used as basis of calculation, is safely for you to assume the first compound in the chemical reaction is your A. Means N2 to A, H2 to B, ammonia to C. Okay, so maka this H2 is your B. So this 60 mole % is actually your YB0. YB0 to 0.6. Hence, YA0, my nitrogen gas is my A, my YA0 is 0.4, sorry. So kamu kena tengok, be very careful, sometimes they give you 20%, sometimes you get confused mana A, mana B. Just tengok the chemical equation, first compound tu adalah A. So N2 to A, H2 to B. So yang 60 mole % ni YB0 0.6, YA0 0.4. Third, satu lagi benda yang kamu boleh perasan. Dalam kes ni takkan ada inert sebab dia kata initially hanya ada hydrogen dengan nitrogen. And so this both hydrogen and nitrogen memang involved in the reaction. There are no other species yang involved dalam reaction tu. Hanya ada hydrogen, nitrogen, ammonia. So you only got 3 compounds in your system. Okay, so that's one more information you have to be very careful to determine berapa banyak compound dalam sistem tu adalah hanya 3 sebab there's no other inert in the question. Okay, next dia kata carry out in a 20-liter batch reactor. So they give us the volume of the reactor as 20 liter. Your V equals to V0 equals to 20 liter. Sebab reactor volume tu you run before after volume the vessel is still 20 liter. Dia kata with 10 molar of nitrogen gas. Okay, so if you remember, molarity stands for concentration, or we can say molarity is mole per liter or mole per dm cube. Okay, so this gives us a concentration. Tapi concentration of what? Dia kata concentration of nitrogen gas. Nitrogen gas is our A. Okay, lepas tu you might think CA ke CA not? Sebab concentration of A kan, concentration of nitrogen kan dia boleh jadi initial, dia boleh jadi remaining. Lepas tu tengok balik ayat, dia kata is carried out in a 20 liter batch reactor with 10 molar. Means dia tindak balas ni dijalankan dalam reaktor dengan menggunakan 10 molar of nitrogen gas. Hence, this is your CA0. Okay, so kenapa CA0? A, nitrogen gas is your A. And dia kata dijalankan, baru nak dijalankan. So, initial concentration. CA0, 10 molar. Okay. Next, let's go to the question. Dia kata the first question, construct a stoichiometric table. All value should be in function of conversion X only by numerically evaluating all other symbol. So dalam part ini dikata disuruh kita buat table, of which in the table all the symbols must be replaced with numbers except for your X. Sebab dia kata in a function of conversion. Maksudnya segala benda dalam table tu dalam bentuk nombor, except for your X, you can leave it as it is. Because nilai X pun dia tak beri. Kalau kita tak tahu conversion, we cannot replace the X value. So the X remains as it is. And next dia kata, soalan kedua, determine the outlet or remaining concentration for all species if the conversion 40%. Okay, dalam part A buat table, part B cari concentration, and part B baru dia beri kita conversion. Maknanya conversion dia 0.4. Okay, tak apa. Kita start dulu dengan buat table. Okay. So, in order to do the table, ni yang part yang paling kena faham. For table, for batch reactor, selagi you tak tahu NA0, you cannot start the table. Or let's say you understand the information wrongly. Okay, let's say tadi kita kata yang 10 molar tu adalah CA0. Let's say you thought that was NA0. So kalau you thought wrongly, you put NA0 as 10, the whole table is already wrong. Means you are wrong at the very first step, the whole table tu dah salah. So make sure you really understand information, and without knowing the real information, you cannot find the value. Sugi, I have to go now, Sugi. I will continue the class lepas ni. Sorry Sugi, I have to leave. Ya, Sugi. Sorry Bye-bye. Sorry, I got emergency kejap.
Okay, doktor.
Sorry The video can be recorded, so later nanti the rest can actually watch the recording. So sorry lah sebab biasanya memang my class is only on Saturday. Just that kena rush sikit sebab by next week I have to do one test. Next Saturday lah as we discuss, because I need to submit certain markah untuk our mid examination board. So kita kena report lah certain markah. That's why got no choice, saya kena habiskan sikit. Actually chapter 3 sajalah. The test will cover chapter 1, chapter 2 and chapter 3. I know that some of you miss some class, tapi okay je, no problem for me. Just that make sure nanti tengok balik slide and then catch up by the video. Macam tutorial video tu saya dah letak dalam Teams. So by right kalau tengok video tu, kalau buat soalan should be okay lah. Kalau faham soalan tutorial, test should not be a problem for you guys lah. Alright. So today I will continue for chapter 3. So last Saturday saya dah cover half part. Now I cover another half of chapter 3. So tak panjang lecture kita malam ni. By right about 1 hour plus. We already settled for chapter 3. Okay. So for chapter 3, what I did last Saturday, we already learned a few things. We already learned about rate law. We also learned how do we actually dapatkan rate law tu for each of the reaction. And then in the rate law, they have a few variables, which is actually first is reaction rate constant, pemalas kadar tindak balas, K. You learn about reaction order. You learn also about elucidating the reaction rate. Sebab when we want to design reactor, when we're talking about designing reactors, we actually need to determine first the rate law. So chapter 3 ni sebenarnya it teach us first how to get the rate law. Then chapter 4 baru kita akan design reactor. So why do we need to know rate law? Because each reaction tu dia ada its own characteristics. As you know, reaction is very diverse. Okay, and then you know as well that reaction ni ada mekanisme yang berlainan, so different mechanism, different rate law. So when you know the rate law, we know how to determine the rate law. Then masuk chapter 4, baru kita tahu macam mana kita nak determine the design of the reactor. Right. So for today, one of the important things needed in the rate law is concentration. So kita kena belajar. We need to learn how to determine the concentration. Right. So dalam rate law tu ada terms concentration. If you realize concentration of your reactant, Ca, Cb. So kita kena belajar how do we elucidate this concentration. So you know, right? Dalam in the reactor you have reactant. Okay, so kita akan monitor concentration dia. We need to learn how to actually determine the concentration. Okay, so before we go towards the concentration, last Saturday I dah ajar how to find concentration if it's batch reactor. So today we will learn how to elucidate concentration if we have flow reactor. So you learn kita ada we learn 3 types actually, but the one that we focus is 2 types. So we learn CSTR, continuous stir tank reactor. One more is plug flow reactor. Okay, so these 2 reactors are called continuous flow reactors. So we want to learn how to determine the concentration. Okay, then next, when we want to determine concentration for flow reactors, CSTR, PFR, they got additional challenge because now you have to really determine and check whether dia adalah gas ke ataupun liquid. Meaning your reactant, the chemicals that you are using, are you in your reactors, are they liquid phase or gas phase? Okay, because the calculations or the elucidation ataupun formula dia dah tak sama for liquid dengan gas. Okay, why is not the same? Because if it's liquid, alright, we have the assumption that volumetric flow rate liquid ni inlet dengan outlet tak berubah. So don't forget, continuous system ni maksudnya is continuous, the reactant is continuously pumped into the reactor and simultaneously is pumped out from the reactor. Okay, so kalau liquid, we can safely assume volumetric flow rate tu, laju isi padu tu, in and outlet, inlet outlet is the same. So memang betul lah laju isi padu cecair, memang inlet dengan outlet tu akan sama. However, if for gas system, this no longer apply. Flow rate inlet dengan outlet for gas phase ni dah tak equal. Okay, why it's not equal is because you know, right, in the case of gas, they are very highly sensitive to few variables, particularly of course pressure. So if there's a pressure change, okay, definitely inlet outlet volumetric flow rate pun dah tak sama. Temperature change as well. Okay, and then third is the chemistry of the reaction itself. Okay, so kalau tindak balas dia melibatkan gas, dia dah tak straightforward. Inlet volumetric flow rate and the outlet volumetric flow rate is no longer equal. Okay, sebab tu nanti kita akan belajar dia ada equation yang relate inlet outlet volumetric flow rate. Disebabkan that phenomenon, that's why bila kita nak determine concentration, dia dah tak sama inlet and dia dah tak sama concentration between liquid phase and gas phase. Okay, so now let me go to the next one. Okay, however, in order for us, okay, in order for us to determine the concentration, first thing first, kita kena buat, we have to construct what we call as stoichiometric table. Okay, so saya tunjuk dulu, saya pergi forward sikit. Saya tunjuk dulu stoichiometric table. Okay, this is what we call as stoichiometric table. Okay, so memang kalau you see the table, you find it very confusing, which is very, very true because when I'm teaching you, I have to teach in terms of symbol. So kalau in terms of symbol, memang it looks very complicated. complicated, very complex, very difficult. Tapi jangan lupa, however, later when we learn the real examples, okay, when we apply it, it will be in terms of numbers. So bila tengok dalam bentuk number tu, it become easier for you to understand. Tapi kalau dalam bentuk simbol ni memang nampak memang sangat susah. Okay. So maybe the question is, kenapa kena buat table ni? Okay, so this table, okay, one thing first, this table will help us to determine concentration. Tu benda pertama. Kita kena buat table ni, information table ni, we will use to determine concentration. First, one thing. Second, this table is actually also a mass balance table. So saya rasa you have learned before about mass balance kan. Biasa dalam reactor ataupun dalam any equipment, it's very important to know mass in, mass out. Sebab preferably we do not want any loss of mass in the equipment. Okay, preferably we want, kalau we put in 10 kilogram, we also want the out is also 10 kilogram. So knowing mass in, mass out monitoring is very important, especially in reactors. Okay, so sama konsep dia. But dia dah tak straightforward in comparison to other kind of equipment, because dalam reactor kan, dalam reactor reaction will takes place. So when reaction takes place, you know konsep dia, kalau reaction takes place, reactant will be consumed. Reactant kena bertindak balas, baru kita menghasilkan produk. Okay, so maknanya reactant punya mass tu harus berkurangan, barulah mass produk tu akan terhasil, baru tindak balas tu berlaku. So nak to determine the mass balance tu dah tak straightforward. Sebab tu kita boleh guna table ni, and the table is powerful in the sense you just need to know, dia macam formula lah, tapi formula dia pun sebenarnya kalau when you learn it, you can find that actually dia ada dia punya persamaan. So you understand one, the rest are about the same. Okay, but let me explain first. Jadi kita nak buat table ni. Okay, so first of all, this table has dia ada row, dia ada column lah kan. Okay, so I explain one by one. Okay, so first of all, species. So species ni adalah to refer to all the compound yang exist in the system during the reaction. Okay, so dia asalkan masa dalam reactor tu, that compound exists in the system, tak kisahlah sama ada dia terlibat dalam tindak balas ke atau tidak, but if it's in the system, dia akan ada baris dia tersendiri. Dia got its own row. Okay, so kenapa? Sebab kan dia mass balance. Mass balance maksudnya every mass has to be accounted for. Setiap benda, setiap compound yang ada mass dalam reaktor tu, kita kena ambil kira dalam pengiraan mass balance dia. Sebab tu each compound, even if dia tak terlibat dalam tindak balas, but they exist in the reactor, you will have its own row. Okay, so contoh dalam case ni, I have 4 compounds. Okay, we have 2 reactant, A and B tu reactant, bahan yang bertindak balas. C and D is your product, what you get after the reaction. So setiap compound tu ada baris dia sendiri. So A, so species A, 1 compound, species B, species C, species D. And then last one, you see that I put I, inert. So maksudnya katakan there are compounds that is in the system but not involved in the reaction. Normally we call it as inert. So inert, I think you know right, lengai. Maksudnya benda tu ada dalam sistem tetapi dia tak bertindak balas. Okay. So kalau dia ada dalam sistem, so that's why kita akan ada satu row untuk dia, khas untuk dia, kalau there is an inert in the system. Okay, so a very simple example of which you will see this is normally kalau reaction that involve oxygen gas. Okay, so of course, in certain reaction, people may consider using pure oxygen. However, for example, if your reaction is like combustion, the reaction which is I would say not significant, ataupun reaction yang basic one, people will not use pure oxygen. Rather, they will use air. Sebab air contains oxygen, so and air is readily available. However, you know, dalam air, not only they have oxygen, dia pun ada nitrogen. Basically, about 79% nitrogen, 21% oxygen, a little bit of carbon dioxide. Okay, so kalau guna air, kita tahu dalam air tu, kita nak guna oxygen tu untuk combustion. Tetapi, you know, in the air has nitrogen gas. So, nitrogen gas tu will not react but nitrogen gas will be in the reactor. So kita akan letakkanlah nitrogen gas tu sebagai inert. So kita akan kira juga the mass of the oxygen gas. Okay, then next. Right, so the calculation of the mass in this reactor sense, we are calculating in terms of mole. Okay, dia bukan dalam terms weight, tapi terms mole, bilangan mole. Okay, but not bilangan mole only, but we talk about molar flow rate, halaju molar. So why kita tak boleh kira dalam bilangan mole? Because it is a continuous system. Kamu tahu kan, kalau sistem tu continuous, flow in, flow out, every calculation is towards time, terhadap masa. Sebab tu instead of mole, dia jadi mole per masa, molar flow rate. So kita akan kira mass ni in terms of molar flow rate. So that's why kamu tengok ada F. F tu signify molar flow rate. Okay, so kita tengok F. The whole table is in terms of F. So kenapa F? Sebab kita akan kira in terms of molar flow rate. Okay, so that's one. Okay, then before I forget, column pula. You can see here we have 3 column. Kenapa 3 column? Sebab kita nak buat mass balance kan. So the first column will be initial. Kita nak tahu how much the molar flow rate initially in. Kan mass mesti ada in, ada out. So first column ni to address berapa bilangan mole ataupun molar flow rate originally before the reaction takes place for every compound. Sebab tu kalau kamu perasan, kita ada FA0. FA0 is apa? A, compound A. This not is actually time 0. So FA0 adalah initial molar flow rate of A. So kita nak tahu waktu asal, sebelum tindak balas berlaku, berapa bilangan what is the molar flow rate of A initially. Then we have B as well. So kita pun nak tahu how much molar flow rate of B initially. C, D and inert. Okay, nanti formula tu saya terangkan kemudian, but I terang first the symbol. Okay, so we have FA0, FB0, FC0, FD0, FI0. So the A, B, C, D to denote the compound. The not is important to indicate this is measured before reaction takes place. Lepas tu, row yang paling last adalah total initial molar flow rate. Sebab mass balance ada in dan out kan, total in, total out. So kita nak tahu berapa total in molar flow rate for all the compounds before reaction takes place. Okay, then the next column is change. So kenapa kita satu column change? Sebab saya kata mass balance in dengan out saja. So kenapa ada column change ni? Sebab this is a reactive process, reaction. So kamu tahu dalam reaction means certain compound which is our reactant will have to be consumed. Baru produk akan terhasil, ataupun in other words, my reactant has to decrease in order for my product to be formed. So column change ni adalah untuk kita tahu berapa perubahan molar flow rate untuk setiap compound semasa tindak balas berlaku. So naturally, kalau reactant, perubahan dia adalah negatif lah. Dia akan semakin berkurangan molar flow rate dia sebab dia dah bertindak balas. Then on the other hand, kalau produk, of course lah, perubahan dia dengan masa, the molar flow rate will increase because they will kept being formed. So reactant continuously reacted, product are continuously produced. So satu akan berkurangan, satu lagi akan menaik. Okay, so that's the change. And then lastly is remaining. So remaining tu adalah out dia lah. So kita sekarang nak tahu what's the molar flow rate after the reaction has taken place. So kalau kamu perasan, initial I put FA0. So remaining become FA. Not tu dah hilang because the not is to indicate initial. So since I want to measure after the reaction has taken place, that's why we put it as FA. So remaining molar flow rate of A. So sama FB, FC, FD, Fi. Meaning kita nak tahu what's the remaining molar flow rate for compound A, compound B, compound C, compound D and compound I. And then lastly, the last row, FT. So FT is the total remaining molar flow rate. Okay, so kita tahu total remaining total molar flow rate initial. Kita pun akan tahu total molar flow rate remaining after the reaction has taken place. So tu konsep dia dulu, apa dalam table tu. Okay, now bagaimana kita nak kira? So you understand the concept, kita nak tahu berapa bilangan molar flow rate yang masuk, berapa molar flow rate yang bertukar, and berapa molar flow rate yang tinggal. Tetapi how do we calculate it? Okay, how are we going to calculate it? Because you know, kalau dalam real application, kita tak akan monitor everything, right? In reaction reactor, we will not monitor all the molar flow rate. It's also impossible to do so. So normally what we do is, dalam reactor, okay, we will only monitor or we will only measure the molar flow rate or concentration of one compound, which we call it as compound A. So compound A itu apa? Sebab this is quite general, right? Okay, katakan if your reaction has one reactant ataupun satu saja reactant lah. Of course reactant tu kita panggil sebagai A. Kita dah gelarkan dia sebagai A. Ataupun maknanya segala pengiraan akan berdasarkan perubahan compound A ini. However, if you have two compound, macam mana? Sebab satu akan jadi A, satu akan jadi B. So, how do you decide mana A, mana B? Okay. So, kalau you learn in reaction, normally kalau kita ada tindak balas yang melibatkan two compound, we will have what we call one as a limiting reactant, one is excess reactant. Ataupun erti kata lain, salah satu, bila kamu ada tindak balas, you put in A and B. Okay, the reactant yang habis dulu tu we call as limiting reactant. Sebab kalau dia habis, tindak balas dah tak boleh berlaku. So we call it as limiting reactant. So limiting reactant itulah kita akan jadikan dia sebagai A dan kita akan monitor ataupun we will record or we will measure its concentration, its molar flow rate, so on and so forth. Okay, so that's how we choose mana A, mana B. Okay, then next. Let's say kalau tak ada access, tak ada limiting, kedua-duanya habis pada waktu yang sama, equimolar. In that case, you have to decide yourself lah which compound you want to choose in as A, which one you to choose as B. Okay. However, you might ask, kalau dalam soalan ke, test ke, exam, macam nak tahu kan mana A, mana B. Okay, that's why in the test or exam or even when you refer to literature or when you read Google or any information regarding reaction, they will always tell you which compound are the basis of calculation. Sebab pengiraan reaction ni, design reactor ni mesti berdasarkan hanya basis of satu compound. Okay, so compound ni is what we call as compound A. Maknanya pengiraan semua akan berdasarkan compound ini. So for example, let's say your reaction, I use a real example. Let's say ammonia production is from nitrogen gas react with hydrogen gas and 2H2 produce ammonia. Okay, so which one is your A, which one is your B? Nitrogen gas A ke hydrogen gas your A? So you have to check from the literature, from the report or from the question. They will write, let's say they write N2 nitrogen gas is used as the basis of calculation. Maksudnya nitrogen gas itu adalah your A. So means all the calculation yang melibatkan pengiraan semua akan melibatkan A. The A is actually nitrogen gas. So maknanya molar flow rate A, molar flow rate nitrogen gas tu akan digunakan sebagai basis of the calculation. Okay, so come back to this. Right. So you can see here, actually all the calculation ada dalam bentuk FA0 and also X. So X tu apa? X adalah conversion. So conversion juga is based on compound A. So FA0 tu apa? FA0 adalah initial molar flow rate of A. X conversion maksudnya just by knowing initial molar flow rate A, FA0, and tahu conversion, kita dah boleh actually construct the entire table. Okay, so how do we do that? That's why let me explain. Okay, but before I go there, we talk about conversion first. So kalau you all are not too sure, conversion tu is, we are talking about kita nak quantify how much our reactant A is converted into product. That's why kita akan kira conversion, which is X. So konsep conversion ni adalah sama dengan how much A reacted over how much A I fed to the system. That is the concept of conversion. Berapa yang telah habis bertindak balas, berapa A yang habis bertindak balas, terhadap berapa A yang saya swap ke dalam sistem or I feed into the reactor. That's conversion. Okay, so now let us try to look how the table is constructed. So first, initial for A, initial molar flow rate of A, FA0. Okay, there we go. Kita pergi row by row is easier to understand. Okay, next. Change. So how much A yang berubah or how much A changed during the reaction is as much as minus Fa0X. So first of all, kenapa ada minus? Sebab dia kan akan berkurangan. Molar flow rate A akan berkurangan sebab A akan bertindak balas. So sebanyak mana dia akan berkurangan? Sebanyak negatif Fa0X. Okay, so for example, katakan, I give example, Fa0, let's say you pump in, the initial molar flow rate is 10 mol per minute, let's say. Okay, so initially kamu prepare 10 molar per minute of A. So lepas dah dia bertindak balas, berapa banyak ia telah bertindak balas? Okay, it will be minus times 10 times conversion X. So let's say lah conversion kamu tu 40%. Katakan 40% conversion means 40% Fa0 tu telah bertukar menjadi produk. So your X jadi 0.4 lah. Okay, because percentage when we want to calculate, we will change into fraction. So negative 10 multiply with 0.4, you got 4. Maksudnya berapa banyak Fa0 yang telah berkurangan adalah sebanyak negatif 4. Dia dah berkurang sebanyak 4. So kalau kita letak hanya 4, itu bermaksud dia tambah 4. You have to put negative 4 to mean dia dah akan decrease sebanyak negative 4 mol per minute. So that's how much A change during the reaction. Then you go to remaining. Sekarang kita nak tahu berapa yang tinggal after the reaction. So become Fa equals to remaining paling senang. You just tengok initial Fa0, you copy change minus Fa0x. That's why become Fa equals to Fa0 minus Fa0x. Ataupun dalam if you are given in terms of number, tadi kita kata initial 10. Change kita kira 4 kan, tolak 4 kan. So it become Fa equals to 10 minus 4, 6. So berapa A yang tinggal after reaction, molar flow rate dia adalah 6 mol per minute. So kalau kita tengok simbol a bit confusing. Tapi when we talk about numbers, dalam erti kata number, it become easier to understand. Berapa yang saya pump in initially 10. Berapa yang telah habis bertindak balas, negatif 4. Berapa yang tinggal, 6. 10 tolak 4 jadi 6. Okay, so that's how we calculate the initial, the change and the remaining. Okay, then but kita pun juga kena belajar sikit juga dalam erti simbol because later we will use this knowledge to elucidate concentration. Yang ni molar flow rate. Kita akan guna table ni untuk buat concentration. So kita kena belajar jugalah simbol dia. So we already learn Fa equals to Fa0 minus Fa0x, initial minus change. And kalau mathematically, kalau saya bawa keluar Fa0 dalam bracket become 1 minus x, tutup bracket. Okay, done. So kita dah tahu macam mana kita nak express Fa in the terms of Fa0, in the terms of x. Okay, now we go to B. So part B ni sikit pening. Okay, why pening? Dia ada formula dah. Okay, so macam dia tak se-straightforward A. A tu senang sebab A tu macam straightforward. B ni dia ada macam, untuk compound B ni dia ada formula sikit dah. Macam mana kita nak mengira. Okay, now in this example, B is a reactant. So maksudnya logically, initially, B akan ada molar flow rate dia. Sebab B tu raw material kita kan, sebelum tindak balas berlaku, B dah kena ada dalam reaktor. So means Fb0 tu akan ada nilai. So kita nak tahu berapa banyak molar flow rate B yang masuk. Kalau tadi A 10, what about B? How much is the molar flow rate? So don't forget, dalam table ni, assumption kita tak kira ataupun kita tak monitor, kita tak measure molar flow rate compound lain. Kita hanya kira untuk case A sahaja and kita nak guna information yang A tu untuk tahu compound yang lain. So that's why this table is very powerful. Saya nak tahu molar flow rate compound lain tapi saya tak payah measure compound tu. Saya tahu A punya molar flow rate, saya tahu conversion, saya dah boleh kira untuk compound yang lain. Tapi they have certain formula yang kita kena ikut. Okay, so let me go to B. Jadi kita nak kira. So they put here Fb0 equals to Fa0 tapi dia multiply with theta B. So ada satu lagi simbol baru. So kalau kamu perasan when you look through the notes for the other chapter, kamu akan tengok macam reaction ni banyak simbol, which is I agree. Dia banyak simbol dan simbol ni kalau kita tak faham ataupun kita tak ingat, memang kita takkan dapat tahu apalah titah ni. So that is the actually challenge of reaction. Tetapi the good part I suppose is dia sampai chapter 4 sajalah kamu akan belajar simbol-simbol yang baru yang memeningkan. After that chapter 5, 6, 7, 8 tu dah macam how do I say, you will keep using the same thing. Just like the first few chapter ni is challenging in that sense. Memang kalau student-student lain pun memang dia akan cakap lah macam reaction challenge dia adalah banyak sangat simbol dengan maksud yang kamu kena tahu. So and you get confused when you got too many. Okay, so let me try to explain in a simpler way. So dia ada theta B. So apa tu theta B? So in a simple way, okay, saya tunjuk slide yang ke belakang. Dia ada terang, kita nak tengok tu theta B. Okay. Theta B ni dalam erti kata yang paling senang nak terangkan is the ratio nisbah initial amount of B over initial amount of A. Nisbah asal bahan B terhadap nisbah asal bahan A. So you realize I cakap bahan. Kenapa cakap bahan? Sebab these numbers can be different depending on the questions, depending on the situation as well. Sebab you can calculate theta B if you are given the mole percent pun kamu dah boleh kira theta B. Maksudnya katakanlah you know initial dalam sistem dia adalah 50% 50 mole percent A, 50 mole percent B. Okay, so melalui mole percent ni pun kita boleh kira theta B. So maknanya theta B akan sama dengan 0.5 divided by 0.5, theta B jadi 1. Ataupun dia kata initially, let's say dia kata initially I have 30 mole percent of B, 70 mole percent of A. Normally kita akan tahu mole percent ni sebab bila reaction kita mesti akan determine first. Kita akan set, kita akan control mole percent ni berapa. So let's say dia kata 30 mole percent B, 70 mole percent A initially. So theta B akan become 0.3 divide by 0.7. Itu adalah nilai theta B kamu. Ataupun let's say you know initial concentration. So waktu asal bila kamu prepare tu, kamu tahu you prepare let's say A initial concentration dia 2 molar, 2 mole per liter. B you prepare 5 molar, 5 mole per liter. So you can also calculate theta B dia. So theta B dia akan jadi 5/2. Dapat theta B dia. So nisbah, cara nak kira theta B ni, dia konsep dia nisbah asal bahan B terhadap A. What is this nisbah asal bahan? Bergantung. Mole fraction pun boleh, initial concentration pun boleh, initial molar flow rate pun boleh. Asalkan maksudnya katakan you have question or you are looking for literature, you are reading about the reaction, you just make sure you know apakah itu initial amount yang diberi ataupun apa maklumat yang you know. What information that is you know. So that information asalkan it is bahan B, the initial amount of B over initial amount of A. Okay, so let's say you calculated theta B. Okay, let's say dah katakan you know initially dia adalah equal molar. Equal molar maksudnya apa? Katakan kamu letak 5 molar per A, 5 mole per liter A, 5 mole per liter B. So theta B dia akan jadi 1 kan? Okay, so theta B 1 you multiply with the FA naught. So contohnya tadi kita kata FA naught kita 10 kan? Kita set 10. So 10 multiply with theta B, let's say 1. So FB naught jadi 10 mole per liter, 10 mole per minute jugalah. Means saya pump in 10 mole per minute of A and 10 mole per minute of B as well. So tapi dia bergantunglah, tak semestinya equal molar flow rate. So certain case maybe they will pump in double, so on and so forth. Okay, so that's how you determine initial molar flow rate of B. So remember I told you, just tahu FA naught, kita tahu initial amount nisbah tu, kita dah boleh kira FB naught. Kita tak measure pun molar flow rate B tu. Kita tahu FA naught, tahu theta B, kita dah boleh tahu initial molar flow rate of B. Okay, then I go to change. Okay, dalam case ni kita pun nak tahu how much B change during the reaction. Okay, to know how much B change during the reaction, kita kena fikir sikit. Dalam kes ni, dalam tindak balas ini, in this reaction, as I show the chemical equation, B is reactant. B mesti berkurangan. Molar flow rate B mesti berkurangan. Kalau molar flow rate B tak berkurangan, tindak balas tak berlaku. So, that's one thing that you always know in reaction. Kalau reactant tak berkurangan, means tak adalah tindak balas yang berlaku. It has to be consumed for the product to be formed. So naturally, that's why dia ada negatif juga macam A sebab dia akan bertindak balas. Tetapi you dah tak boleh straightforward terus minus FA0X macam A. Kita kena ambil kira perkadaran stoichiometric coefficient or the ratio of stoichiometric coefficient. So what is stoichiometric coefficient? It is the number in front of the compound in the chemical equation. So katakanlah tindak balas dia, chemical equation kata 1A react with 2B. So let's say they write it 1A plus 2B. So B per A dia will become 2/1. So 2/1 multiply with FA0 multiply with X. So let's say I use the previous example. Let's say B per A is 2/1 multiply FA0 10 multiply with X 0.4. So you will get actually 8, negative 8 minus 8 mol per minute. Maksudnya berapa banyak molar fluorid B yang bertindak balas? Sebanyak negatif 8 mol per minit. So tadi asas 10 kan? 10 B yang masuk. Berapa B yang bertindak balas? Negatif 8 yang telah habis. So naturally berapa B yang tinggal? FB jadilah 2. 10 minus 8 become 2. So berapa molar fluorid B yang tinggal lepas tindak balas? Only 2 mol per minute. Okay. Tapi itu terms a number. In terms of symbol, how do we write it? So become FB remaining molar fluoride of B equals to FA0 theta B. Macam mana nak ambil? Kita ambil je initial and then you combine with the change minus B per A FA0X. Combine je. So memang kalau tengok simbol you find it a bit hard. Tetapi kalau I talk about in terms of number, you can find that it's so much easier sebenarnya. Tapi sebab tu kita kena tahu simbol dia sebab simbol tu adalah formula dia. Okay. Then the same thing I do. Mathematically, I take out the FA0. Kamu tahu kan matematik, kalau kedua-dua variable tu ada variable yang sama, you can take out. So, become FA0 in bracket theta B minus B per A X tutup bracket. So, now we already know how to get FB. Kalau kamu perasan, just by knowing FA0, theta B, initial amount ratio tu dengan X kita memang tahu sebab conversion tu daripada part pertama kita tahu B per A is from chemical equation. Okay, done. Now we go to C and D. Okay, so C and D ni hampir sama sebab C and D is our product. So kita ingat kan tindak balas berlaku, reactant consume barulah kita dapat produk. So produk dia C and D. So kalau you think logically, initial molar flow rate for C and D mestilah kosong because initially they are not formed yet. Dia perlu tindak balas berlaku baru dia boleh terhasil. So initially takkan ada molar flow rate C, takkan ada molar flow rate D. Okay, tapi jangan lupa pula, okay, tindak balas ni adalah we call it as irreversible, tindak balas yang tak berbalik. So kamu kena faham juga, sometimes certain reaction dia ada yang berbalik. So berbalik konsep dia dah lain sikit. Tapi kita hanya address for tindak balas yang tak berbalik. So means it's only forward, meaning A and B will react and then I will get C and D. So naturally pada waktu at minute 0, at time 0, I will not have molar flow rate of C, molar flow rate of D. Okay, sebab tu FC0, FD0, 0. Okay, then I go to change. So, berapa banyak perubahan molar flow rate C dan D? So, naturally, sebab dia adalah produk, dia mesti akan terhasil. Dia akan semakin bertambah semasa tindak balas berlaku. That's why you see I will have a positive sign to signify it will be keep added to the reactor. Added is always going to be formed more and more as the reaction goes by. So, it become plus C per A pula. So tadi B per A sekarang become plus C per A FA0X again. So C per A ni adalah konsep sama. The ratio of the stoichiometric coefficient in your chemical equation. So the C is the number in front of compound C in the chemical equation. The A is the number in front of compound A in the chemical equation. So katakanlah contohnya let's say C per A ni adalah 1,1. Contohnya 1A react with 2B to produce katakan 1C. So C per A tu 1 lah kan. So 1/1 multiply FA0 let's say 10. Let's say multiply X 0.4. So jadi 4. So berapa banyak C yang terhasil? Sebanyak 4 mol per minit. So kalau kamu perasan, berapa banyak A yang hilang? Negatif 4 mol per minit. Berapa C yang terbentuk? 4 mol per minit. So that's the concept seperti kita buat mass balance. Kita nak tahu berapa banyak A yang telah habis, hilang, untuk kita tahu banyak B, berapa banyak produk yang terhasil. Okay, so that will be the change. Right. So then next, berapa C yang tinggal selepas tindak balas? So how much C remains after the reaction? We put it FC. Tadi FC not initial, remaining FC. So berapa banyak FC yang tinggal? Of course lah, equal kepada berapa banyak C yang terbentuk tadi. Sebab dia tak ada awal kan, dia hanya ada dalam sistem tu bila tindak balas berlaku. So of course the remaining for C is just equal to the change. Okay, ataupun kalau kita confuse, tengok FC sama dengan initial 0 combine dengan change plus C per A FA not X. Sebab tu you remain as plus C per A FA not X. Then same for D. So D pun konsep yang sama, just that beza dia, kita kena tukarlah stoichiometric coefficient dia berdasarkan D. So you have to check the chemical equation. What is the stoichiometric coefficient for D? You will use it to get the change for D. Okay, so perkadaran stoichiometrik ni, I think you remember lah, kita kena buat imbangan elemen. Kita tahu, okay, katakan contohnya macam katanya N2 reaction dia nitrogen gas, hydrogen gas menghasilkan ammonia. Kalau untuk persamaan tu menjadi balance, it has to be N2 plus 3H2 to get 2NH3. So imbangan the stoichiometric coefficient tu have to be balanced. Then only you can do this calculation. Okay, then next one we go for inert. So inert pun sama. We need to know initial molar flow rate inert. So initial molar flow rate inert, kalau you realize, is about the same like B. Okay, maksudnya Fi0 is initial molar flow rate inert. So I put I. So I tu is just to indicate dia inert. Tapi kalau compound sebenarnya nitrogen gas katakan, so kita akan kira lah sebenarnya bilangan molar flow rate nitrogen gas. Just that kita letak sini simbol inert. Okay, so how much initial molar flow rate of inert equals to again Fa0, tetapi now dia multiply with theta I. So kalau tadi theta B, ni sekarang theta I. Tetapi konsep dia masih sama. It's the ratio of amount of inert over amount of A. Kalau tadi initial amount of B over A, now become initial amount of inert over A. So katakanlah in your case you have A, B and inert. So let's say I give you example. Let's say the mole percent asal A is let's say 40%. Okay, mole percent A asal 40%. Katakan B is 30%. Katakan mole percent inert yang baki 30%. So ada 40, 30, 30 baru 100%. Itu dalam mole percent dia. So berapa theta B? So theta B will be equal to 0.3 divided by 0.4. Dapatlah theta B. Kira guna kalkulator. Theta inert will be again 0.3 sebab dia 30% juga. So 0.3 divided by mole percent of A, 0.4. So mole fraction, sorry. 0.3 divided by 0.4, you get your theta I. So tak semestinya lah theta B, theta I ni sama, tak semestinya. It depends on the initial mole fraction dia lah yang kita tengok daripada sistem, or how much you decide the mole percent will be. Dan ataupun as I told you, kalau dia bagi concentration pula, dia beritahu kita concentration asal inert is let's say 3 molar. Concentration asal A is 5 molar. So theta I equals to 3 divided by 5. So tak kisah pun bagaimana information tu diberi, nisbah dia akan sama. So dia bagi concentration, kita guna concentration. Dia beri mole fraction, kita guna mole fraction. Either way, you will still get the initial molar flow rate of inert. Okay, then next. Change. So kamu tengok sini, I letak 0. Kenapa? Because naturally inert is not involved in the reaction. Kalau kamu tengok persamaan reaction pun, persamaan tindak balas, there's no inert, right? There's no I. Because the I is in the system, but they are not involved, or they are not involved in the reaction. They will not change. They will not be consumed. They will not be produced. Bilangan molar flow rate dia akan sama. Sebab tu takkan ada change. Then, that's why naturally, the remaining molar flow rate of inert akan sama dengan initial molar flow rate of inert. So, initial remaining molar flow rate of inert will not be different because there are no change of inert during the reaction. So done for inert. Okay, then lastly, you will have to calculate the total initial molar flow rate. So example just now I told you, katakanlah F naught tu 10. FB naught ni katakan lagi 10. So 10 mole per minute, 10 mole per minute. Let's say inert, let's say lah 5 mole per minute. So total initial 10 plus 10 plus 5 is 25. So total initial molar flow rate FT naught, T to indicate total, F molar flow rate, not initial, 10 plus 10 plus 5, 25 mole per minute. Subsequently, remaining pun sama. You have to calculate. You have to jumlahkan initial molar flow rate of A, molar flow rate of B, molar flow rate of C, molar flow rate of D. Then you will get the total molar flow rate for the whole system. Okay. So done on stoichiometric table. Okay. Tetapi tak habis lagi. Okay. Kenapa tak habis lagi? Sebab okay, the table that we learn just now, dia kalau you understand reaction ni is very diverse. Okay, sebab tu reactor design is a very complex process because reactions are diverse. Okay, tadi yang example yang I taught you is when you have two reactant. Sebab naturally reaktan pertama tu A, reaktan kedua tu B. Sebab tu I always have to teach in terms of A, B, C dan D. Sebab I cannot teach you based on the real reactant. Kalau real reactant, nanti kalau kita tukar reaktan kita dah confused. Sebab tu we always teach in general A, B, C and D. Okay, so the previous example, the two reactant was A and B. Okay, so let's say now in this example, okay, I still want to do the stoichiometric table. However, now I only have one reactant. Let's say your reaction now involve only one reactant and you get two products. So tadi A and B was the reactant, C and D was the product. In this example now, let's say A is my reactant, B and C is my product. Beza dia sekarang, B sekarang dah bukan reactant tapi B adalah product. So kalau example macam ni, you have to understand, for the stoichiometric table, the B is already different. Okay, dalam stoichiometric table tu, how we want to measure the molar flow rate of B is no longer the same anymore because the previous example, B was a reactant, B bertindak balas. In this example, when B is a product, B akan terhasil. Okay, so apa yang berubah in terms of B? You can see the initial molar flow rate of B now becomes 0. Kenapa initial molar flow rate of B becomes 0? Because B is a product. Initially, I will not have any molar flow rate of B as they are not yet produced during the reaction. So FB naught becomes 0. The change. Kalau tadi the change for B was a negative, dia akan berkurangan sebab dalam contoh tu B is a reactant. So reactant has to be consumed. So the molar flow rate of B will decrease. Okay. However, in this example, as B is now product, the molar flow rate of B will continuously increase because they will keep being produced. That's why it becomes plus B per A FA naught X. Kalau tadi minus B per A FA naught X, now it becomes plus B per A FA naught X. Simply because it will continuously produce in the reaction. Hence, remaining dia pun dah lain. Okay, so the remaining FB, kalau initial FB naught, remaining FB. So how much FB remain? Ataupun how much FB we get after the reaction? Of course lah, equals to how much the change just now. Okay, so FB equals to change plus B per A FA naught X. Okay, berapa banyak B yang tinggal selepas tindak balas adalah sama dengan berapa B yang terbentuk during the reaction. Initial kita dah tak consider sebab as I told you, initially memang takkan ada B dalam sistem sebab B belum terbentuk or not yet produced during the reaction. Okay, so that's how we understand the table or how we want to determine molar flow rate of all the compound initially, how much it changed and how much it remains after the reaction. Okay, so now what is important is why do we need the table? So I told you tadi awal-awal, first thing table tu we use for mass balance. Okay, in terms of molar flow rate, kita tahu balance berapa initial, how much it change, how much it remains. Second is we need this table information because kita nak tahu rate law dia. So rate law is actually minus RA. So why nak tahu minus RA? Because later in chapter 4, I will teach you how to design reactor. So nak design reactor ni, you really need to know first minus RA. Kalau untuk reaction tu, you don't know minus RA, kita tak boleh tahu, we do not know how to determine minus RA, you will not be able to calculate or design the reactor. So one part of the minus RA rate law tu, do refer to the notes part awal chapter 3 tu. In this rate law minus RA, kita nak determine they are the concentration. Okay, so we have to use the table to determine concentration. Kita nak cari, tadi we learn molar flow rate kan, kita tahu molar flow rate A, molar flow rate B, molar flow rate C, molar flow rate D, FB, FA, FB, FC, FD. So I want to use this information from the table to now determine concentration CA, CB, CC, CD. So table bagi FA, FB, FC, FD. Saya nak cari sekarang kepekatan pula CA, CB, CC, CD. So dia tak straightforward. So macam mana kita nak tahu daripada molar flow rate yang tinggal tu kita nak translate kepada concentration. Okay. Konsep dia tak susah. Tetapi cabaran dia, the challenge is to determine the concentration pula, as I told you tadi, dia sekarang bergantung. Are you finding the concentration for liquid or concentration for gas? So it's always, I think, quite challenging in reactor design kalau if you are talking about gas phase system. Sebab tu nanti you kan tengok pengiraan untuk design reactor gas phase ni is completely different and more difficult in comparison to liquid. Sebab tu what I know is most of the time memang liquid reactions are easier, gas phase reactions are very difficult. Dan lagi susah kalau liquid gas reaction you have multi-phase, tu lagi cabaran dia. Okay, tetapi now we address first kalau liquid phase and then kita address gas phase. Okay, now kenapa dia berbeza? Okay, macam tadi saya kata purely because volumetric flow rate. Halaju isi padu. So if you're talking about liquids, the volumetric flow rate, initial and outlet ataupun initial and remaining, I can say that also. Initial remaining volumetric flow rate, if you're talking about liquid, dia adalah equal. Maksudnya, if you pump in initially, katakan kamu ada reactor A and B kan, so kamu pump in initially 10 liter per minute, halaju isi padu, 10 liter per minute of liquid A and B. After the reaction, you still get 10 liter per minute mixture of compound C, compound D, product C, product D, ada juga reactant A, reactant B. So regardless campuran compound tu, isi padu, halaju isi padu tu akan sama in dan out for liquid. Tetapi is no longer the same for gas. Tapi part tu nanti kita will touch later. Let us touch about liquid first. So liquid, volumetric flow rate are the same inlet and outlet. Okay, so based on that assumption, it influences our calculation. Sebab tu chemical engineering is a very interesting branch of study because you need to understand the chemistry or the chemical phenomenon to explain or to elucidate your equation. So equation tu matematik. Tapi pengiraan matematik tu berubah disebabkan chemical phenomenon. So what do I mean by this? Okay. Sekarang kita nak elucidate concentration, kan kita nak tahu concentration daripada molar flow rate FA, FB, FC, FD. I want to find concentration CA, CB, CC, CD. So let me do first for A. So concentration of A, CA. C subscript A to signify concentration of A. So concentration of A equals to, kalau you remember this, dia ada perkaitan. Concentration, molar flow rate, volumetric flow rate, they have a correlation of which concentration of A equals to outlet molar flow rate of A. CA ni outlet concentration of A, ataupun bila saya cakap outlet, saya cakap remaining sama. Maksudnya kepekatan atau molar flow rate selepas tindak balas. Kalau ada not, dia means sebelum tindak balas. Kalau dia tak ada not, maksudnya dia tak ada simbol kosong tu, maksudnya semasa ataupun selepas tindak balas dah berlaku. So, outlet concentration of A equals to outlet molar flow rate of A divided by outlet volumetric flow rate. Dia mesti outlet, outlet, outlet. So, berapa outlet concentration of A sama dengan outlet molar flow rate of A divided dengan outlet volumetric flow rate. Okay, so FA ni from the table, that's why we do the table. Sebab daripada table, it tells us FA ni equals to FA naught in bracket 1 minus X. So that's the function of the table. Dia beritahu kita FA itu adalah sebenarnya sama dengan FA naught in bracket 1 minus X. So I replace my FA with FA naught in bracket 1 minus X. Okay, then per. So per tu, it's disebabkan chemical phenomenon explains that volumetric flow rate doesn't change for liquid. Inlet, outlet volumetric flow rate takkan berubah untuk liquid phase system. So, I will write the outlet volumetric flow rate as inlet volumetric flow rate. So, this one we use the symbol epsilon. Okay, so epsilon tu actually to indicate volumetric flow rate. So, kamu tahu kan C concentration, F molar flow rate, epsilon dia macam V. Tapi sebenarnya tak boleh guna V sebab V adalah volume. So, kita guna epsilon. So, now it become epsilon naught, inlet volumetric flow rate. So kita bukan tukar sebarangan. We change it from outlet become inlet volumetric flow rate because chemically it is understandable volumetric flow rate liquid tak berubah. Okay, then why we do this? Because when I have FA naught at the top, I have epsilon naught at the bottom. This can be divided. It becomes CA naught. So sekarang saya dah dapat CA, the outlet concentration in the form of initial concentration of A dalam bracket the 1 minus X tu masih ada. So sekarang saya dah boleh express kepekatan A. I already express the outlet concentration of A. So it becomes CA equals to CA naught in bracket 1 minus X. Means I want to know outlet concentration of A. If I know initial concentration, I multiply with the conversion. I dah tahu berapa kepekatan A after the reaction has taken place. So done for A. Okay. Now we do for B. So pemahaman dia sama je. Kita guna table, kita dapat information tu, kita guna untuk elucidate the concentration. So concentration of B. So concentration of B pula, it depends. Adakah in your reaction B is a reactant or in your case the B is a product? Dia dah berlainan. Kenapa? Sebab tadi pun kita buat table, I explain to you, we got two different table kan. Table pertama bila B is a reactant, table kedua bila B adalah product. So sebab FB tu dah berlainan. When B is a reactant, FB tu dah berlainan. Bila when the B is a product, the FB is different. Okay, so what's the difference? Okay. First, let's say we do kalau B is a reactant. So outlet concentration of B equals to outlet molar flow rate of B over outlet volumetric flow rate. So kalau tadi CA equals to FA divided by epsilon. Kalau CB becomes equals to FB over epsilon. Still over outlet volumetric flow rate. Okay, then FB remaining molar flow rate of B. Just look at the table. Tadi daripada table kita dah belajar. So daripada table kita tahu FB is equal to FA naught in bracket theta B minus B per AX. So I replace for my FB and then because of the chemical phenomenon that I have explained, outlet volumetric flow rate sama dengan inlet volumetric flow rate. So I replace with inlet volumetric flow rate. I replace dengan epsilon naught. Instead of epsilon, saya ganti dengan epsilon naught. Then sama konsep, saya ada FA naught di atas, I got epsilon naught di bottom, I can divide, I get CA naught back. So become CA naught in bracket, yang dalam bracket tu tak berubah. So become in bracket theta B minus B per AX. So sekarang kita dah express outlet concentration of B when B is a reactant. So equals to CA naught in bracket theta B minus B per AX. Okay, so then next. For produk pula, katakan B adalah produk. Okay, so same concept. Part pertama tu masih sama. Outlet concentration of B equals to outlet molar flow rate of B divided by outlet volumetric flow rate. Tetapi bila B adalah produk, from the table, FB now equals to plus B per A FA naught X. Sebab tu jadi plus B per A FA naught X divided by outlet volumetric flow rate. So again, saya ada FA naught di atas, saya ada V naught epsilon naught di bawah. I divide, I get CA naught. The remaining is still the same, so become plus B per A CA naught X. So sekarang kita dah express untuk CB. Okay, so kalau kamu semua rasa macam ni sangat memeningkan, saya boleh faham tak? I really can understand sebab I really have to teach you in terms of simbol dulu. Memang kalau bila saya ajar simbol ni memang memeningkan. Tetapi later I will show example and then tutorial question, you can really see sebenarnya dia tak susah pun bila ganti dengan nombor. Tapi kalau macam ni belajar dengan simbol memang susah. So don't worry too much. You're not expected juga untuk hafal. Saya told you right, memang open book. Even kalau face-to-face physical exam pun memang for reaction. I never ask my student to memorize formula sebab tak guna pun. Yang penting as you guys are working, you know the important is nak tahu nak apply equation. Macam mana kita nak apply kalau reaction ni, kita nak solve masalah dia, macam mana kita nak guna equation. So the same concept in my course, you are not expected to memorize all this. Sebab nanti kalau test minggu depan, final exam pun memang open book. I allow you to open everything that you want. You can open, you can refer. Tapi yang penting kena faham. So tu yang part yang mencabar sebenarnya, nak faham tu, nak apply dalam soalan tu sebenarnya part yang mencabar. So when this lecture, if you feel you're lost, it's very very normal, then tak apa pun sebenarnya. Tapi I will do tutorial this Saturday sebab apa yang saya cover sampai Sabtu ni akan keluar untuk test lah. So I will really help you for the test. I understand it's challenging as well to work and to handle study, especially reaction ni memang last semester pun saya ada student flexi learn, and surprisingly you will be shocked, flexi learn students actually did well. I would say equally top actually flexi learn students and also the normal students. So sebenarnya very very doable kalau memang faham course tu memang okay. So this Saturday I will cover the tutorial part sampai part test. So if you can turn up for this Saturday tutorial, much better, about 9 o'clock. Tapi tak apa, if you cannot turn up pun it's okay. I will do the video recording. Tapi you have to refer lah video recording tu untuk faham. Because I will really explain in the tutorial. Memang tutorial style saya memang student dia buat bersama-sama. So means I will really explain the step. I will really show you the step. So you will look and then you will try to do it together. So kalau tak boleh catch up pun tak apa. So if you cannot turn up pun tak apa. You see the video, you can attempt by yourself. Kalau faham, should be no problem for your test next Saturday lah. Tapi if any one of you yang tak boleh datang untuk test ke sebab kerja ke apa, just inform me. We can arrange different time. Tetapi cut point dia saya kena submit markah pada 14 hari bulan 4. So test I plan to do 10. But let's say you cannot turn out 10, you want to do later, you want to do earlier, just contact me. Just that last point, cut point tu 14 tu saya kena submit markah. So you have to do the test before 14. And the test is only 90 minutes. Tak susah pun sebenarnya. To be fair to all, memang tak susah pun the test. But just inform me lah if you cannot do it on 10 hari bulan 10 hari bulan tu, Sabtu depan. Okay, so I come back to this course. Okay, I come back to this lesson. So sama, we will calculate for C, D and E naught. Kita pun nak buat benda sama. Kita guna table, information from the table. You'll be able to elucidate the concentration for C, concentration for D and concentration for the E naught. Okay, tetapi I think the best way is let me explain example. So I habiskan sikit part yang teori sikit, then I will explain the example. Hopefully I have time. Tapi kalau sebab saya pun tak nak pergi lama sangat, because I know kalau malam ni susah sikit. So not only for you, for me also it's very difficult kelas malam ni untuk lama-lama. So I will finish first the theory. Kalau sempat kita bincang soalan. Kalau tak sempat Saturday, I will push forward the question. Okay, so next part is, tadi kita dah elucidate concentration for liquid. So you know concentration of A, B, C dan D and E naught for liquid. Okay, now part yang susah sikit sebab kita nak buat benda yang sama tetapi sekarang is for gas. So gas ni yang sebenarnya susah because for the case of gas, volumetric flow rate, laju isi padu, inlet dengan outlet ni dah tak sama. Okay, dia tak sama sebab as you know, gas phase system are always influenced by a lot of variable, especially pressure, temperature, and of course, the chemistry of the reaction itself. So, someone has already come up with a correlation. So, katakan kamu nak tahu laju isi padu gas yang selepas tindak balas yang keluar pada reaktor kamu, sebenarnya dah ada equation yang kamu boleh guna untuk tahu. As long as kamu tahu initial, kamu dah boleh kira. Okay, so the correlation is given in this equation, in the yellow box equation. Unfortunately, part yang susah sikit, equation dia kompleks. And then equation ni pun ada lagi simbol-simbol yang kamu kena faham. Sebab tu memang at first, very normal, sudah akan rasa reaction ni susah, which I totally agree sebab dia akan ada banyak simbol, banyak pengiraan, banyak equation, banyak sub-equation. Tetapi, I will explain it slowly for you to understand. Okay, so the equation says that outlet volumetric flow rate, epsilon naught, laju isi padu, kau bayangkan kamu nak tahu berapa laju isi padu gas tu, outlet tu equals to initial volumetric flow rate. So kalau gas, kalau liquid kita dah berhenti kat sini. Kalau gas kita tambah part yang belakang tu. So become initial volumetric flow rate untuk gas in bracket 1 plus epsilon x. Okay, x tu kamu dah tahulah conversion. So memang dalam reaction ni we will always talk about conversion because we always would like to know how much my reactant A is converted during reaction. The higher the conversion, the better it is. Sebab tu, ideally kita nak 100% conversion. All reactant converted into product. But you know, usually that's impossible. So that's why orang guna catalyst, orang design better, more efficient reactor, so on and so forth. Okay, so X tu kamu tahu. Epsilon ni another new symbol that we have to learn. Okay, tapi I will explain later apa tu epsilon. Okay, so epsilon ni simbol baru. Epsilon ni pun dah equation, ada sub-equation lagi. So calculation of epsilon is something quite difficult, but I will explain later. Okay, but I will explain first the back part. So the back part ada P naught per P. So P naught per P ni is to address pressure change during your reaction. So kamu tahu kalau gas phase reaction, there are chances or there are tendencies to have pressure change. So kalau ada perubahan tekanan, of course volumetric flow rate pun akan berubah. Okay, sebab tu dia akan include P naught per P. So again, naught tu maksudnya apa? Initial pressure. P, final pressure or pressure semasa tindak balas berlaku. P naught tu tekanan sebelum tindak balas berlaku. P is tekanan semasa atau selepas tindak balas berlaku. So if your reaction has pressure change, you have to include the P naught per P. So you have to understand, tak semestinya semua gas phase reaction ada perubahan tekanan. If you have in your reaction, it occurs, kita tambah P naught per P. Tetapi kalau tak ada perubahan tekanan, mean in your reaction there are no pressure change. So P naught per P ni jadi satu lah sebab P naught akan sama dengan P kan, tak ada perubahan tekanan kan. Let's say P naught 5 atm, P pun 5 atm. So P naught per P jadi satu. So you don't have to really include P naught per P in the calculation. Next, T per T naught. So T naught initial temperature, T is the remaining temperature during or after the reaction. So you know, reaction pun ada pula reaction isothermal, non-isothermal. So isothermal, iso means same, thermal means temperature or heat. So kalau isothermal means no temperature change, means masa tindak balas berlaku, temperature tu masih sama. So kalau itu berlaku, we call it isothermal. So T per T naught ni jadi satu jugalah. Tetapi if your reaction is non-isothermal, meaning semasa tindak balas berlaku isothermic ke, endothermic ke, or sometimes you supply heat to the system, so of course akan ada perubahan suhu. So then adalah nilai T dan T naught itu. Okay, so kalau ada, then you have to include the T per T naught. Kalau tak ada, tak payah include T per T naught. Okay, done. Next, I explain epsilon. So epsilon ni, kenapa ada terms dalam bracket ni 1 plus epsilon x? Sebab the chemistry of the reaction itself influence the volumetric flow rate for the case of gas. Sebab kamu tahu kan gas ni dia is very different from liquid. Gas ni even in the reaction itself tu dia punya jenis tindak balas pun akan mempengaruhi your volumetric flow rate. So to calculate epsilon ada sub-equation lagi. Dia ada dua dalam satu equation. Okay. Epsilon is equal to Y-E0 sigma. So tambah satu lagi simbol. Okay, apa tu Y-E0? So Y-E0 I think you have probably if you dah tengok chapter sebelumnya, kita dah belajar Y-E0. So Y to indicate mole fraction. A untuk compound A, not is initial. So Y-E0 is initial mole fraction of A in the system. Okay, so contohnya katakan if your reaction satu reactant sahaja, reactant A, of course lah Y-E0 tu 100% 1. Okay, kita biasa guna cakap in terms of percent, calculation jadi fraction. So 100% Y-E0 is 1. Okay, ataupun you guna pure A, Y-E0 1. However, let's say your reaction got two reactant, katakan reactant A, reactant B. So definitely lah Y-E0 takkan satu sebab ada juga mole fraction from B. So katakan the system, the reaction is 40 mole percent A, 60 mole percent B. So Y-E0 tu jadi 0.4. Okay, so Y-E0. Multiply with sigma. So sigma ni pula tambah satu lagi simbol. And sigma pun ada lagi equation dia. So that's why memang that's the challenge of reaction. That's the challenge of reactor design. So kalau kamu perasan subject reaction is one of the rare course of 4 credit hours because reactor design is very complex. Okay, so now you will realize kenapa sebab pengiraan dia pun dah tak straightforward. Sebab tindak balas ni, kalau fasa ni, okay, pengiraan dia kena tambah lagi faktor-faktor lain yang we have to consider. Okay, so what's sigma? Sigma is basically the ratio of your stoichiometric coefficient. So, stoichiometric coefficient itu adalah nombor di hadapan compound dalam tindak balas. So, the ratio stoichiometric coefficient ni pula, kalau kamu perasan saya letak ada tambah, ada negatif, ada tolak, ada tambah. Kenapa? Because always konsep dia dalam reaction, produk adalah something yang always akan bertambah. It will always be positive for the product. It will always be negative for the reactant because konsep dia reactant kena kurang baru produk akan bertambah. So in terms of stoichiometric coefficient pun konsep yang sama. Sebab tu kamu nampak dalam first example, the reaction is between two reactant, two product. C dan D is the product, A and B is the reactant. So it become plus D per A, stoichiometric coefficient of D over stoichiometric coefficient of A, plus C per A, stoichiometric coefficient of C over A, minus, dah jadi minus. Kenapa? Dah untuk reactant. So minus B per A, minus 1. So kenapa minus 1? Technically is A per A. So A per A itu 1. That's why it will always be minus 1. A itu sentiasa akan jadi reactant. Tak mungkin A will always be reactant. That's why dia akan jadi minus A per A minus 1. However, this is the part that makes reaction difficult. Formula sigma ni tak fix. What do I mean by tak fix? Okay, example dan the one that I'm telling you now is the case where A and B is reactant. Tetapi remember I told you, there are certain reaction di mana satu reactant sahaja. Means A is my reactant, B saya sekarang mewakili produk. Okay, so when B is a product, the sigma calculation for part B tu dah menjadi plus. Kalau tadi negatif sebab B adalah reactant. When B is a product, it become positive. So become C per A plus B per A minus 1. So kamu tengoklah persamaan kimia dia. Katakan persamaan kimia dia 1A menghasilkan 1B, 1C. So it become 1 per 1 plus 1 per 1 minus 1. So 2 minus 1 jadi 1. So sigma is 1. Okay. So that's how you calculate sigma. That's how you calculate epsilon. That's why you can calculate how to get the correlation inlet-outlet volumetric flow rate. Okay. Tapi belum lagi. Kita nak cari concentration. Okay. Now, as I told you. Okay. Although this correlation relates pressure change, temperature change, but you must remember equation ni boleh berubah, depends on your reaction. Meaning, if let's say your reaction has your reaction is constant temperature, isothermal. So part T per T naught ni dah tak ada. Fenomena kedua, let's say dia adalah constant pressure. Kalau constant pressure tak ada perubahan tekanan, part P per P naught ni tak ada pula. Katakan your reaction has no pressure change, no temperature change. So part yang belakang P naught per P, T per T naught ni pun tak ada. So you can see equation dia tak fix in that sense. Kamu kena betul-betul faham soalan ke, in the real application ke, equation chemical engineering ni, that's the complexity because equation dia boleh berubah mengikut phenomenon that is occurring in your system, or in my case in the reactor. So although this equation is given to me, but this equation can be shortened, can be elongated depending on the nature of the reaction that happens. So macam dalam exam, dalam test, reapplication, sama konsep. Equation tu kamu kena betul-betul faham bagaimana dia boleh berubah dan kenapa dia berubah depends on the nature of your reaction. Okay, so I come back to my lesson here. Now, saya buat balik apa? Saya nak express balik concentration. Tapi, saya nak express balik concentration untuk gas. Tadi saya express untuk liquid, now saya express untuk gas. So, kenapa dah berlainan? Sebab tadi, remember, kalau tadi, outlet volumetric flow rate terus sama dengan inlet volumetric flow rate kan, tetapi sekarang dah tak sebab dia dah gas phase. That's why dia jadi inlet outlet volumetric flow rate sama dengan inlet, betul, yang belakang 1 plus epsilon x P naught per P, T per T naught. Okay, so let me explain one time again. Okay, so now I want to find concentration of A, tetapi this is gas phase. Okay, again tadi saya express untuk liquid, now I express untuk gas. So the first step masih sama because outlet concentration of A equals to outlet molar flow rate of A divided by outlet volumetric flow rate. So step pertama ni gas atau liquid sama je. Kepekatan sama dengan molar flow rate terhadap volumetric flow rate. Okay, then equals to FA, you have to check from the stoichiometric table. Sama konsep, FA from table masih sama. Bila kita buat table, liquid gas same table, just that we express the concentration dah berlainan sebab of the volumetric flow rate. So FA equals to FA naught in bracket 1 minus X. So I replace at the top, okay. At the bottom, I replace now the outlet volumetric flow rate equals to inlet volumetric flow rate in bracket 1 plus epsilon X P naught per P, T per T naught. Okay, so then same concept. I got FA naught at the top, outlet volumetric flow rate at the bottom. I can divide, I get CA naught. So CA naught yang selebihnya dah masih sama. So I just replace. So in other words, kalau for me to simplify it in a simplest way, kalau liquid, kamu hanya ada yang part atas. Pasal tak tadi part atas CA liquid, CA equals to CA naught in bracket 1 minus X. Tetapi sebab dia gas, dia tambah yang pembawah tu, yang 1 plus epsilon X, P naught per P, T per T naught. So part yang bawah ni ingatlah, kalau no pressure change, P naught per P tak ada. No temperature change, T per T naught tak ada. So it depends on your system. Okay, so kita dah express untuk A, kita express juga untuk B. So konsep masih sama sebenarnya. So I don't have to explain more in detail. Just that, apa yang berbeza for the gas phase is that pembawah dia tu kita dah tambah part 1 plus epsilon X P naught per P, T per T naught. Bahagian atas tu sama je. Tapi kalau liquid, concentration dia part atas tu sama. Kalau gas, kena tambah yang part pembawah ini. Okay, so again as I told you, memang simbol ni nampak kompleks. Okay, nanti kita buat soalan. You can see that it's actually not that complex. So this is CB, CC, CD, CI. Okay, so for me to better explain, I will explain one example that we are done for today. So sebab sekarang dah pukul 9.30, one example we are done for today. Okay, so maybe you will understand better and I feel better if I can help you to understand one example first. Okay, so let's say here, set up a stoichiometric table. So kita buat table for the following liquid phase reaction and express the concentration of each species in the reaction as a function of conversion, evaluating all constant. Okay, so dia kata disuruh kita buat table. Dan daripada table tu, they ask us to use a table to determine the concentration untuk each compound. Dalam contoh ni, this is ethylene oxide, water. Okay, so you get the product. Okay, so dia nak kita tahu, dia nak kita cari the concentration of A, B and C. So I terus guna A, B and C lah. Although it's actually ethylene oxide, water. Okay, so dia nak kita buat table. Daripada table tu, we need to find out the concentration of all three compound in the reaction. However, dia kata for the table and also for the concentration, dia suruh kita express as a function of conversion. Meaning, disebabkan in this example, dia tak boleh kita nilai X. Maksudnya pengiraan kita semua dalam bentuk number except X tu kita biarkan sebagai X sebab kita tak tahu berapa conversion dia. Sebab tu dia kata as a function of conversion because we don't know what's our X value. So the X is leave as it is, the rest are numbers. Okay, then dia kata lagi information. The initial concentration of ethylene oxide and water in the flow system. So ni adalah liquid flow system. So kamu kena ingat juga kan, penting untuk tahu ni adalah liquid atau gas. Sebab nanti kita nak express concentration. Is 1.5 mole per liter, 4.5 mole per liter. So now I know initial concentration ethylene oxide dan initial concentration of water. So ethylene oxide adalah A, water adalah B. So 1.5 mole per liter tu adalah CA0 sebab ethylene oxide adalah A. So CA0, A is ethylene oxide, not is initial. So initial concentration of A is 1.5 and because water is B, so CB0 4.5. So CA0 1.5, CB0 4.5. So how do I know dia initial? Kan dia kata initial concentration. Okay, next dia kata in addition, molar initial flow rate 10 liter per minute. Okay, so flow rate ni kamu kena faham. Flow rate ada boleh jadi molar flow rate, boleh jadi volumetric flow rate, which we have learned, right? Ada F atau epsilon. So you have to check the unit. Unit dia liter per minute. You know liter is volume, minute is time. Volume per time, volumetric flow rate. So this is actually epsilon naught. Sebab dia kata initial. So epsilon naught is 10 liter per minute. And because this is liquid phase, epsilon naught akan sama dengan epsilon. Means 10 liter per minute yang masuk, yang keluar pun akan juga 10 liter per minute. Then dia kata assume reaction isothermal isobaric, no temperature change, no pressure change. And dia kata use ethylene oxide as basis of calculation. So the last sentence is actually to tell you C2H4O ni, ethylene oxide is your A. Asas pengiraan adalah berdasarkan A. So your A is your ethylene oxide. Okay. So first kita buat table dulu. Okay. So nak buat table. Okay. So first of all kami ingatkan kalau kita nak buat table, in order for us to get the table, kita kena tahu dulu FA0. Kan the whole table in the form of initial molar flow rate of A. So maksudnya kalau nak buat table ni, selagi tak tahu initial molar flow rate of A, FA0, you cannot do the table. Sebab table tu memerlukan information FA0. Tak ada FA0, table tak boleh buat. Okay, so you check back. Are we given information on FA0? So kami ingat balik, FA0 tu molar flow rate, dia mesti mole per time. So if you check question, there is no numbers yang ada mole per time. If you realize, kita ada mole per liter, kita ada liter per minute, tapi kita tak ada sebarang information dalam bentuk mole per masa ataupun katakan contoh mole per minute, tak ada. So means in this question, dia tak boleh kita directly FA0. Initial molar flow rate of A tu kita tak tahu. So means kita tak boleh start table tu tanpa tahu FA0. So how do we do this? Okay. So if you remember, baru kita tadi belajar, kan kita ada correlation. CA0, FA0, V0, kalau kamu remember, if you remember, CA0 equals to FA0 over epsilon naught. Sorry, yang kena saya cakap V0. Jadi V0 tu maksudnya epsilon naught, volumetric flow rate. Sorry. So, you remember just now I said CA0 equals to FA0 over epsilon naught. So, if I want to find FA0, it will be equal to CA0 multiplied with epsilon naught. So, saya tahu concentration, initial concentration of A, saya tahu 1.5. Tadi kan dia kata CA0 1.5. initial volumetric flow rate epsilon naught was 10 liter per minute. Laju asal volumetric flow rate. So kalau you realize, okay, let's say you cannot remember ataupun kita confused, darab ke bahagi, you just do unit cancellation lah. Kamu tahu, kamu tengok penyeraan ni, I can cancel liter. Ada 1 liter di atas, 1 liter di bawah, saya boleh cancel. So become mole per minute. So dapat dah unit yang saya nak, mole per time, molar flow rate. So when you multiply, you get Fe0 as 15 mole per minute. So Fe0 equals to Ca0 multiply with epsilon naught. So after you get Fe0, then kita dah boleh buat table lah. So table tu hanya kita boleh buat kalau kita tahu Fe0. Okay, so let us do the table, a quick one. Okay, so dalam case ni, it's a very simple table because kita ada 3 compound je. 2 reactant, 1 product, tak ada inert. Dia tak cakap apa-apa pun pasal compound lain. So ada 2 reactant, 1 product. So each compound tu has its own row. Okay, so C2H4O, 1 row, water, the second row, the product C2H6O2, the third row. So the row last tu total dia. Okay, so the first one, ethylene oxide. So kita namakan dia sebagai A. Water, B, product dia C. So for initial molar flow rate of A, 15 mole per minute. Tadi kita kira Fe0 15. Okay. Change, berapa banyak A reacted? It was minus Fe0x. Kita tadi belajar formula minus Fe0x kan? So become minus 15x. So berapa remaining? So kalau initial Fe0, remaining Fa. So Fa equals to, kamu tak payah hafal formula pun. Kamu tengok initial 15, kamu combine dengan change minus 15x. Dapat dah Fe. So remaining ni memang tak payah hafal ataupun memang tak payah memerlukan sangat pemahaman. But initial dengan change ni a little bit of understanding. Okay, so next. B. Nak tahu berapa pula? Berapa initial molar flow rate of B? So the initial molar flow rate of B, formula dia, that's how we learn, is Fa0 multiply with theta B. So Fa0 15. What about theta B? How do we find? Theta B is initial amount of B over initial amount of A. Ataupun, erti kata lain, initial amount of water over initial amount of ethylene oxide. So dalam example, what they gave us was the concentration. We know initial concentration of water 4.5 mole per liter. Initial concentration of ethylene oxide 1.5. So 4.5 divided by 1.5, you get 3. So theta B 3 multiply with 15. Molar flow rate B initially is 45. Ataupun erti kata yang paling senang, nisbah A dan B yang masuk adalah 1 terhadap 3 daripada nisbah ni. Sebab tu kalau molar flow rate A yang masuk 15, molar flow rate B yang masuk kali 3, 45. Sebab nisbah dia 1 kepada 3. Sebab tu concentration dia, nisbah dia 1.5 to 4.5, right? 1.5 of A to 4.5 of B. So kalau molar flow rate dia pun 15 untuk A, 45 lah ke untuk B darab 3. Okay, done. So how much change of B? So how much change of B? Berapa banyak B yang telah bertindak balas? Okay, so formula dia minus B per A Fe0x. So again dalam contoh ni, soalan ni, X ni, dia tak tahu, kita tak tahu nilai dia. Sebab tu kita kena tinggalkan nilai X tu sebagai X. So minus B per A, you look at the stoichiometric coefficient. It is 1A reacting with 1B or 1 ethylene oxide with 1 water. So B per A dia 1 per 1. So net minus 1 per 1 multiply with 15, the Fe0, multiply with the X, you get minus 15X. So initial 45, change berapa banyak water change or react, minus 15X. So how much water remaining? Fb equals to initial 45, copy the change minus 15X. So Fb equals to 45 minus 15X. Done for B. So next one, C. So for C, initially no molar flow rate. Again, sebab C product. Initially takkan ada molar flow rate C. So the change for C sekarang jadi plus because C is a product. So plus C per A, Fa0x. So C per A pun masih 1 because you see the reaction 1A, 1B, 1C. So C per A is 1, FA0 is still 15, X is still unknown. So kita biarkan, so become plus 15X. So berapa remaining C, FC, remaining molar flow rate of C become equals to the change 15X. Initial tak ada kan? So initial tak ada, terus copy the change 15X. Then the last one, total. Don't forget, kita is still a mass balance table. Total in, total out tu kena tahu. So total in, tambahkan sahaja 15 plus 45, 60. Total remaining ni, susah sikit sebab total remaining ni, dia ada nombor, dia ada X. So konsep dia, nombor tambah dengan nombor, yang X tu tambah dengan X. So maksudnya, total remaining become 15 plus 45 dapat 60. So tambahkan 48X. So minus 15X. Plus minus 15x plus 15x, you will get minus 15x. So total remaining ni adalah 60 tolak 15x. So again, kenapa? Sebab kita tak tahu x. So kalau dalam soalan tu kata dia beri nilai x, kamu gantilah dengan nilai x. Kalau dia tak beri, then you remain the x as it is. Okay, then last one for today, for tonight. Okay, kita nak cari concentration. So concentration is the easiest part. Sebab ni liquid phase kan. Okay, so concentration dia, that's why kita buat table. Kita guna table untuk cari concentration. So outlet concentration of ethylene oxide, Ca, equals to outlet molar flow rate of A divided by outlet volumetric flow rate. Fa from the table was 15 minus 15x. Ambil je per table. Volumetric flow rate, sebab liquid, outlet, inlet, volumetric flow rate sama. So I will use 10. So you divide, you get 1. Kamu ingat kan kalau nombor kena, kalau ada 2 pengatas, 1 pembawah, kedua-dua pengatas tu kena bahagi dengan nombor di bawah. So 1.15 divided by 10, 1.5. 115x divided by 10, 1.5x. Sebab tu kamu dapat 1.5 in bracket 1 minus x. So katakan, you know the value of x, you will replace the value of x. Okay, so next, reactant B, okay, CB, outlet molar flow rate of B, outlet concentration of B equals to outlet molar flow rate of B divided by outlet volumetric flow rate. So from the table, FB equals to 45 minus 15x. Sebab table tadi kita dah tahu FB sama dengan 45 tolak 15x divide by the volumetric flow rate. Okay, so nombor dengan nombor, X dengan nombor pembawah, kedua-dua pengatas kena bahagi dengan pembawah. You get 4.5 minus 1.5x, and subsequently for C, you will get 1.5x. So in this example, again, a bit complex sebab kita tak tahu nilai X, conversion. However, if you know the conversion value, then this is purely numbers already. Okay, so that's all for tonight. Dah memang hampir pukul 10 pun. Actually, I suggest you all can tahan nanti pukul 10. It's actually quite a hard topic for me to cover at night. Sebab tu saya prefer kelas hari Sabtu. Sebab I avoid kelas malam sebab I rasa reaction to do at night is quite difficult especially. Tapi sebab nak test kan, so macam saya kena rush sikit lah. Tapi don't worry, if you cannot, I hope you can attend the Saturday tutorial, but tak boleh attend pun tak apa. Tapi make sure tengoklah video, catch up. But if you have problem, you need more assistance, please inform me. I will try to help as much as I can. Okay, I will explain a little bit later, tapi saya rasa bukan malam ni lah, Sabtu ni saya akan explain pasal lab juga, what will happen for your laboratory. Okay, so that's all for tonight. But before I go, ada soalan ke ataupun ada apa-apa komen ke, ataupun kamu semua pun dah penat juga malam ni? Ada apa soalan tak?
Sekarang macam tak ada lagi doktor. Rasa kena buat tutorial dulu lah, baru macam clear sikit.
Betul. Faham. Okay. So Zubairi dengan Azudin okay ke?
Okay doktor. Macam Kamil.
Okay doktor.
Alright, so nanti kita buat tutorial lah Sabtu ni. Tapi kalau tak dapat datang, saya kata lah saya akan record video. So if you know my style untuk flexible ni, I'm quite flexible. So masa saya faham kalau kamu tak datang kelas, it's fine. Tapi saya make sure saya prepare all resources. Nanti kamu catch up lah. Tapi ada masalah, please inform me. Okay, so that's all for tonight. Have a good rest. Tolonglah pergi rest. Saya rasa kamu semua mesti dah penat. So I will see you on Saturday hopefully. Okay, take care. Have a good night.
Thank you doktor.
Bye-bye.
Okay doktor.